When the Milky Way's dark heart quietly sculpts jets, bubbles, and newborn suns, how many hidden fingerprints of that unseen artist remain for us to find? In the deep, inky silence at the heart of our galaxy, there are whispers, not voices of life, but whispers in the fabric of space itself. We drift among swirls of stars and clouds of cosmic dust, far from Earth's gentle twilight, and listen. Amid the quiet celestial sea, something unseen stirs and speaks to us. At the very center, where light itself seems hesitant to tread, an unseen force holds sway, anchoring our galaxy. The stars there sweep in swift, graceful circles, like dancers around a distant, invisible conductor. For us on Earth, making this journey to the galactic core took patience. Early telescopes captured only vague hints, unable to peer through the cosmic shroud that veils the center. Over decades, scientists built new tools, giant radio antennas, X-ray satellites, infrared cameras, and trained them on the heart of Sagittarius. Night after night, year after year, they listened, calibrating and learning. With each new observation, the whispers grew clearer. It felt like tuning an ancient radio, matching the exact dial to catch the faintest signal. Eventually they did catch it, a steady hiss coming from a tiny region near Sagittarius's center. They named this faint beacon Skr A, and each clue coaxed out more secrets about the heart of our galaxy. With patient eyes, astronomers watched the stars themselves, turning on their orbits. Year after year, some of those stars were seen on tight paths, circling ever faster as they drew near the center. Each curve in their flight was a clue, a note in a silent song. By following those loops precisely, scientists measured the weight of the secret at the center. The result was staggering. A mass millions of times the Sun, packed into a volume no larger than our solar system. No known object could hold that much mass in so small a space, except one. A black hole, an invisible sentinel bound by gravity, fit the bill. The star's graceful spins became a cosmic testimony to its existence. In that cosmic hush, our galaxy itself began to tell us what hides at its heart. Its voice was gentle and mysterious. Light and stars moved as though drawn to something unseen. Each motion a quiet message. The more we listened, the clearer the picture became. The center of the Milky Way holds an invisible giant, a dark guardian we cannot see directly. Through patient observation, we came to understand that this silent sentinel holds our galaxy together. In that understanding lies a kind of awe, as if the universe shared a secret just with us. Perhaps the most marvelous thought is this: our galaxy is not alone. Beyond the Milky Way, countless other star cities stretch across the night sky, each with its own hidden story. Where stars cluster and light bends, there may be other silent giants whispering their secrets. The dance we observed in Sagittarius A was just one act in a grand cosmic ballet. As we drift away from our own galactic center, our journey takes us now to seek those invisible monarchs across the universe. Beyond our Milky Way, a universe of distant star cities awaits. Each swirl of stars we see in the night sky may conceal a secret at its core. As we shift our attention from our own cosmic address, we aim to listen to the whispers from afar. Among the nearest is Andromeda, a familiar sister galaxy with its own gathering of stars at the center. Even Andromeda, only a short journey of light away compared to distant quasars, harbors a massive dark heart. Astronomers tracing the motion of its stars have found that, there too, a colossal unseen force sits at the center, bending their paths. Farther beyond, some galaxies shine with unbelievable brilliance. They appear as pinpoints of light, called quasars, outshining everything around them. For a long time, we didn't know what powered these cosmic lighthouses. Then we learned that at the center of each quasar burns a hungry giant, a black hole devouring matter at an insane rate. Its gravity pulls in gas and stars, which swirl and heat until they blaze like cosmic bonfires. This realization was a revelation. Those invisible giants had been broadcasting signals across the cosmos all along. Black holes themselves do not shine, yet nature leaves clues. We look for X-ray flashes, jet streams, and the bending of light around invisible mass. In a landmark achievement, telescopes on multiple continents combined to become one Earth-sized eye. In 2019, this network revealed the first portrait of a black hole, not drawn by visible light, but by the radio glow of dust and gas swirling at the edge of the abyss. A bright ring surrounding perfect darkness, the silhouette of the giant in the galaxy Messier 87, emerged from the darkness. Soon, that same technique was used to hint at the hidden heart of our own Milky Way, a whispered reflection of its unseen core. Each discovery added another piece to the puzzle, yet also deepened the mystery. We have brought the invisible into view, but what we find is still beyond the reach of light and familiar senses. If unveiling these giants showed us their shape, turning our gaze closer lets us contemplate their true nature. Now, we prepare to peer into the blackness itself, toward the dark heart of the galaxy and of spacetime. It is a journey from seeing to understanding, from watching shadows dance to seeking the source of the darkness itself. With each unveiling, one mystery remained untouched: the dark heart itself. Black holes are paradoxical. By definition, no light escapes them, yet all the answers of physics they contain. They are darkness incarnate, yet so powerful they shape entire galaxies. Imagine now that you could stand just outside the event horizon, on the verge of the unknown. Behind you, the light of the galaxy is distorted by gravity, wrapping space into a band of swirling stars. Beyond the horizon, though, lies nothing we can ever see directly, an abyss at the center of existence. The event horizon is the boundary of the unknown, the point of no return. Approach it, and time itself seems to slow. Light tries to flee, but is stretched to invisibility. From far away, any traveler drifting toward a black hole appears to freeze, dripping slowly into darkness. Yet from their perspective, the universe outside races on. It is a quiet transformation of space and time, a whispered magic of relativity, hidden at the edge of the void. Inside the event horizon, the rules as we know them unravel. Physicists say all the matter and energy crumples to a single point, or something stranger yet. In that abyss, density and gravity become infinite, a singularity at the galaxy's core. It is a place where our current understanding of time and space breaks down. We can only theorize what lies there. Perhaps an infinitely small point, or a bridge to another realm. The mystery deepens our fascination, as much as it deepens the darkness itself. One of the greatest leaps came from Stephen Hawking's insight. He showed that black holes are not entirely silent. Even at their edges, quantum effects allow a tiny escape of warmth. Black holes glow with a feeble light, a whisper of heat in a place of ultimate cold. It is unimaginably faint, but in principle, it means these giants can evaporate over time. This idea connected the mysterious darkness to the quantum world, reminding us that even the deepest night has a glimmer of knowledge. Time itself behaves strangely near the dark heart. Clocks on a spaceship falling toward the horizon would tick slower relative to distant stars. An hour close to a black hole could correspond to years in the cosmic suburbs. From far away, our friend's journey would stretch out forever as a fading trail of light. Gravity's embrace is not just pull, it is a distortion of reality itself, bending time along with space. Long before we could see them, Albert Einstein opened the door to black holes. In 1915, his theory of general relativity described gravity as a curve in space and time. Extremes of that curve, places where mass compacts infinitely, were an odd curiosity in his equations. These solutions implied dark wells in the universe, though Einstein himself was uneasy about their reality. Today, we know that the very equations he wrote allow for these deep abysses. He taught us how to understand them without ever using the word black hole itself. Einstein also predicted that massive objects bend light. When light from a distant star passes near a hidden mass, it creates arcs and rings, a cosmic mirage. Now we see these rings in the skies, confirming his insight. Around black holes, the effect is most dramatic. Light from glowing gas warps into a ring at the horizon, exactly as Einstein's equations suggest. Each time we picture a black hole's horizon glowing, we are tracing the curves in spacetime that he described a century ago. In 1916, Einstein predicted another cosmic wonder, ripples traveling through space itself. He thought we might never catch them. Yet a century later, silent instruments heard a faint whisper from the cosmos. In September 2015, detectors called LIGO sensed the passing of space-time ripples from two massive black holes colliding light years away. This quiet thrum, the collision of invisible giants, was the sound of Einstein's prediction becoming reality. Suddenly, we could listen to black holes, as well as see their silhouettes. Even the first image of a black hole's shadow is a victory of Einstein's vision. Imagine all of Earth's telescopes linked to form one eye. That eye looked at M87 and found a dark circle rimmed by light, the very shape predicted by relativity. Einstein's equations were etched into that cosmic portrait. Each new way we uncover a black hole, whether by waves, radiation, or carefully bent light, is guided by the principles he laid down. His shadow is long, shaping every corner of this quest. Our journey toward understanding these cosmic sentinels has traced the path laid by Einstein's brilliance. His equations predicted the darkness at the heart of galaxies and the ripples through the void when those darknesses collide. Every whisper we have heard and every shadow we have seen is in a way Einstein's own. The tapestry he wove with space and time is the map that led us here. Even as we peer into the abyss, it is his language that narrates the tale. In the end, to stand at the threshold of a black hole is to stand in the shadow of Einstein, listening to the silence he foresaw. Black holes hide in the quiet hearts of galaxies, unseen by even the most sensitive eyes, yet their presence is unmistakable. These cosmic titans seem paradoxical. Born from collapse and capable of destruction, they also become engines that set entire galaxies in motion. In the silence of space, a black hole's gravity sings an invisible tune, drawing together dust and gas and guiding them into swirling spirals. Far from being mere voids, they act like cosmic dynamos. At a galaxy's center, Their gravity and turbulent energy help shape the environment. They anchor the galaxy's arms, and their influence channels the chaos of infalling matter into new forms of creation. We once called them devourers, but now we see them as crafters. Picture a galaxy without its central black hole. It might lose its spiral arms or fail to trigger enough star formation. In the quiet ballet of cosmic evolution, these hidden cores play the role of choreographer. They weave the galaxy into being. In this light, the darkness at the core is not empty. It is a source of structure and energy, quietly steering the galaxy's fate. Imagine the early universe. A few 100 million years after the Big Bang, galaxies were forming in bursts of brilliance. And to the surprise of astronomers, even then, black holes were awake. With the James Webb Space Telescope's infrared eyes, we have spotted galaxies so young that they had only just begun to light up. To our amazement, many of these infant galaxies already hosted voracious black holes at their centers. The black holes and the fledgling stars seemed to grow together, feeding each other. In that dawn era, the monster at the center was not an afterthought, but a partner in the galaxy's birth. These revelations came only in recent years. The James Webb Telescope, peering back to the universe's infancy, revealed that many of the very first galaxies had brilliant central engines. We now speak of little red dots in the deep sky, each one housing a feasting black hole amid newborn stars. This was startling. Earlier models had no place for such early black holes. Astrophysicists now believe that to understand the birth of galaxies, one must consider the heartbeat of the black hole at their cores. In the cosmic midnight of time, black holes seem to have served as cosmic midwives, overseeing the birth of new galaxies. Astronomers describe this as a cosmic symbiosis. The birth of stars and the growth of the black hole are entwined in a complex dance. Gas and dust streaming inward provide fuel for both. As stars ignite, they send out winds and shockwaves that nudge more material toward the center, where the black hole lurks. The black hole, in turn, glows brilliantly. Its intense radiation pushes on the surrounding gas clouds. This gentle push can compress those clouds just enough to spark further star formation, even as it clears paths for light to escape. In this way, the galaxy reaps what it sows. Star formation seeds the black hole, and the black hole's fury nurtures more stars. It is a feedback loop of creation, where collapse begets collapse in a self-regulating cycle of growth. This cosmic partnership is a dance of extremes. Stars form and illuminate the galaxy, and in their death throes, they release gas that eventually spirals down to the core. The black hole feeds and flares, while that flare's pressure nudges nearby clouds to collapse. It sounds paradoxical, but this gentle shove can tip a cloud into starbirth. Think of it as a cosmic pas de deux, violent collapse and luminous creation entwined. Astronomers discovered a stunning example, a small dwarf galaxy named Hennes 210. Barely a tenth the mass of the Milky Way, it nonetheless held a powerful secret. Rather than starving of life, the galaxy was ablaze with newborn stars, neon clouds of stardust swirling in brilliant light. At its heart, a black hole quietly fueled this firestorm. Rather than quenching the flame, its energy fanned the nebulae around it. It was as if the black hole had become a celestial hearth, warming its surroundings. In that tiny galaxy, a profound lesson emerged. Sometimes a monster is also a gardener of brilliance. Sometimes the black hole's influence is visible in narrow streams of plasma bursting from the core. These relativistic jets carve through the galaxy like cosmic blowtorches. Far from the center, These jets plow into clouds of cold gas. Under that impact, the gas can collapse and spring new stars to life, as if struck by a bolt of creation itself. It's a paradoxical painting, violence leading to birth. Astronomers have seen rings of star-forming material at the edges of such encounters, halos of young suns born in the jet's wake. In those images, we witness creation after destruction, where the might of the black hole's blast fosters pockets of new life. The accretion disk itself is a crucible of raw power. Spinning around the black hole at unimaginable speed, it grinds matter into energy. Inside this disk, collisions are so violent that particles are flung outward, raining energy back into the galaxy. The hot, inner parts of the disk heat to millions of degrees and glow across the spectrum. A significant fraction of the falling matter is converted to light and high-energy radiation. As it eats, the black hole grows dimmer in mass, but brighter to the universe. Its light illuminates the galactic center like a beacon, a blazing ring of fire in the darkness. We once thought black holes only swallowed and silenced. Now we see how they also speak in light. The brilliance from the disk is often observed as a quasar. These quasars can outshine their entire host galaxy during the feast. In effect, when a black hole eats its fill, it announces itself in a cosmic fireworks display. The galaxy bathes in this radiance, its gas heated and stirred. Elements are forged in this crucible of energy, and clouds glow with a new intensity. In our own galactic backyard, hints of this story can be found. Astronomers have discovered gigantic bubbles of radiation soaring above and below the Milky Way's disk, relics of a cataclysmic event long ago. They believe our central black hole, normally quiet, once blazed fiercely and unleashed energy in all directions. These ancient bubbles tell us that even our galaxy felt the black hole's creative touch. The shockwaves from that outburst would have compressed gas in the Milky Way's disk, possibly nudging new stars to light up. In a sense, our own sun may owe its existence, in part, to that titanic age of creation. On the grandest scales, black holes also help shape the cosmos. When the universe was young, titanic quasars flooded space with energy. Their radiation was so intense, it penetrated the primordial fog of neutral hydrogen. As a result, they helped finish the great reionization of the universe, a transformation that set the stage for galaxies and stars to shine across space. In this way, even the darkest monsters lit the path for cosmic evolution. Even now, creation goes on in layers around black holes. Often, stars themselves gather into compact clusters near the core. These nuclear star clusters glow brightly, as if reflecting the light that the black hole indirectly provided. They may have formed from the same gas that fed the black hole, and that gas was compressed by its influence. Entire stellar populations spring up in the black hole's vicinity, adding to the galaxy's centers of creation. In some galaxies, the region around the core is a stellar nursery, nurtured by the black hole's presence. So far, we have witnessed how black holes can kindle creation. For now, we revel in the beauty they foster, leaving the tale open. Over cosmic time, every flame they fan will also be fed back to them. The brilliance we witness around black holes is not endless. Each star they grant life to will one day spiral inward to feed the beast. But that future feast belongs to the next part of our journey. For now, we bask in how darkness kindles light and how the universe thrives in the wake of its hidden engines. Black holes are always hungry, but their appetite becomes clear when they find a banquet. When dust and gas stray too close, The black hole lures them into orbit. These materials form a glowing whirlpool known as an accretion disk, the black hole's dinner table. The disk heats up fiercely and radiates light across space. In this cosmic banquet hall, the black hole grows fat on every molecule it swallows. As it feeds, the surrounding disk shines more and more brightly, a feasting beacon seen from millions of light years away. In effect, as it devours its meal, the black hole lights up its surroundings. Around the black hole, matter spirals inward, heating up with friction. Astronomers call this the accretion disk, a hot, bright, rapidly spinning circle of gas and dust. It is the black hole's light source. The closer material gets to the core, the hotter it becomes, until it blazes with X-rays and ultraviolet light. This is the fire of the feast. In effect, as the black hole devours its meal, it lights up the night sky. Even though the black hole itself is invisible, the glare from its dinner announces its presence in the galaxy. Sometimes a dinner can be a dramatic event. If a star wanders too near, it can be torn to shreds. These tidal disruption events are true cosmic spectacles. The star is drawn into the black hole's gravity, stretched like taffy, and ultimately engulfed. During this act, the black hole flares dramatically, outshining the entire galaxy for a brief moment. Telescopes catch these flashes as signals of a ravenous meal. One telescope campaign in recent years has doubled the known examples of these star-eating events. Each is heralded by an enormous burst of energy that lights up multiple wavelengths. The discovery of dozens of such star-shredding dinners confirms that black holes are constantly feasting, if only we know where to look. The feast is not limited to stars. Black holes also gulp clouds of gas and dust. In galactic centers, gravity and turbulence funnel giant molecular clouds toward the core. When these clouds reach the black hole, they too spiral inward to join the meal. Some of the gas never falls in. Instead, it is heated and sent back out in winds and jets. But a portion inevitably adds to the feast. Over time, this accretion of material can double or triple the black hole's mass. Every meal, whether star or cloud, makes the black hole grow fatter and leaves behind only the memory of gas and energy. Cosmic collisions serve up the richest banquets. When galaxies merge or pass near each other, streams of stars and gas are flung toward their centers. This galactic turmoil provides fresh fuel for black holes. Astronomers have observed colliding galaxies where one central black hole lit up by consuming the inflowing gas. One dramatic example is a pair of interacting galaxies where a monstrous black hole became a beacon after gobbling material from its partner. Such collisions can transform a quiet black hole into a glutton. When two galaxies dance, their black holes often join the feast and grow to even larger sizes. Even as the black hole feasts, it may eject some of its meal with flair. Often it sends out jets of particles and energy in return. These jets, twin beams travelling at nearly light speed, are like burps after the cosmic meal. They carry away some of the feast's energy and momentum and can extend far beyond the galaxy. But at their source, they testify to the ferocity of the feast. Astronomers know that every luminous jet traces back to a diet of matter, a trade-off of cosmic consumption for energetic display. Our own galactic black hole also leaves clues of its appetite. Astronomers have detected faint echoes of past flares reflecting off nearby gas clouds. These suggest that centuries ago, Sagittarius A had brighter meals, causing X-ray outbursts that illuminated the galaxy's center. Those echoes are like footprints of a feast long past, showing that even here, the black hole occasionally feasts on wandering clouds. Each faint glow captured is a sign that our own sleepy giant once consumed more, lighting up its neighborhood for a brief time. The feeding frenzy can be spectacular. Some black holes become so bright during a meal that they outshine their entire galaxy. In such moments, we call them quasars. These distant lighthouses blaze from billions of light years away. Each quasar's glow is the black hole's banquet made visible. It shines trails through the darkness, a sign that even the brightest beacons of the universe were powered by these hidden engines. We can witness a range of feasting styles, sometimes a gentle savoring, sometimes a violent binge. When gas drips slowly into the black hole, the accretion disk glows steadily, like embers in a vast cosmic hearth. But if a giant cloud of gas plunges in all at once, the black hole erupts in brilliance, a brief volcano of light that fades back to calm as the gas is consumed. This flickering glow is a testament to the feast's unpredictability. The physics of the feast is extreme. Gas swirling into the disk crashes and heats up, reaching temperatures of millions of degrees. At such intensity, even simple atoms break apart and glow as ionized plasma. The black hole's meal becomes a storm of particles and radiation. In a way, matter is sorted by weight. Lighter elements swirl in torches of light, while heavier fragments spiral inwards deeper. Einstein's famous equation tells us a surprising fact. A significant fraction of the infalling matter is converted directly into energy. Thus, as it eats, the black hole grows dimmer inside, but makes the galaxy brighter outside. These cosmic meals are not one-time treats. Over the eons of a galaxy's life, its black hole may feast repeatedly. One by one, gas clouds and stray stars fall to the center, gradually fattening it. Each meal increases its mass. In fact, the supermassive black holes we see today likely became so enormous by countless feasts. They may have started as small seeds, but by swallowing everything in reach, they grew to millions or billions of times our sun's mass. Our own Milky Way's central hole, for instance, is thought to have reached its mass through such slow dining. Astronomers even think our black hole once had an adolescent binge. The glowing bubbles above and below our galaxy's disk, called the Fermi bubbles, hint at an ancient feast. Perhaps a few million years ago, gas poured into the center, causing a burst of energy that carved those bubbles into our galaxy's sky. In that sense, we are living in the aftermath of one of the Milky Way's past meals. These winds of creation can reach staggering speeds. Outflows have been observed traveling at millions of miles per hour, fast enough to fling gas into intergalactic space. Some flows carry ionized gas, others carry cold molecular gas and dust. Overall, these outflows can sweep out the reservoir of fuel that stars need. In a cosmic instant, a fraction of the galaxy's gas can be propelled away. Astronomers have identified structures called X-ray cavities and radio lobes as relics of black hole activity. These look like bubbles blown into the galactic halo, carved by past jets and winds. For example, the galaxy M87 in the nearby Virgo cluster has giant radio lobes, evidence of where its central black hole once inflated balloons of hot gas. In Perseus and other clusters, we see ripples in the hot gas that were likely set in motion by black hole outbursts. Such features indicate that for eons, the black hole's winds have been shaping the gas around galaxies. We have seen how black holes gorge on the galaxy's bounty. Having consumed so much matter, they leave their mark on the galaxy's very structure. The stage is now set for the grand dance of stars and gas. What will the galaxy look like after the feast? How will its stars move and galaxies sway under the black hole's influence? In the next act, we will follow this choreography across the cosmos. Now we turn to the motions that follow the feast. Black holes act as hidden choreographers, governing the grand dance of stars and gas in their galaxies. Though invisible, their gravity and energy shape the orbits around them. In a spiral galaxy, stars circle the center in elegant paths, but close to the core, these paths twist into patterns dictated by the black hole. In our own Milky Way, we see this dance play out. A star called S2 loops around the central black hole every 16 years. When viewed over time, S2's orbit takes on a rosette shape, as if drawn by an invisible spirograph. This intricate track confirms that Einstein's theory of gravity guides the choreography even here. It is a cosmic ballet traced in slow motion, graceful and precise. Around Sagittarius A, dozens of stars perform this ballet. Closer to the center, they swing around at astonishing speeds. Some complete an orbit in just a few decades, hugging the black hole tightly. Their paths are the fastest dances in the galaxy, whirling at millions of miles per hour on an invisible circular stage. Watching them, astronomers can weigh the black hole by the steps of the dance. Astronomers treasure these stellar dances as clues. By charting their orbits, we measure the black hole's mass with precision. Each star's path is a tiny test of gravity. In fact, the more stars we map, the clearer the choreography becomes. New instruments will soon watch even fainter dances near the core, revealing the black hole's every subtle cue. Far beyond our galaxy, another dance has been recorded. In a distant galaxy, two monstrous black holes twirl around each other. The larger one is billions of times the mass of the Sun. Its partner is much smaller. They orbit each other like heavyweight dancers locked in a 12-year tango. Every time the smaller plunges through the larger's disk of gas, a burst of light is sent across the universe. Astronomers watch these flashes as steps in a cosmic dance of titans. Our understanding of gravity would be incomplete if we did not mention gravitational waves. When two black holes finally merge, they send ripples through spacetime. This final pirouette is like silent fireworks, felt by detectors on Earth. While those detected so far are from smaller black holes, the principle is the same. When galactic cores meet, their central black holes will merge too, closing the dance with a gentle rumble felt across the cosmos. The black hole's pull also influences larger-scale motions. It is a small actor compared to the galaxy's overall mass, but at the very center, its gravity adds a twist to the rotation. Galaxies often rotate smoothly around their core, and the inner orbits can be slightly faster if a heavy black hole lurks there. It's as if the conductor of an orchestra steps up to direct the musicians. The melody changes subtly with each cue. Outside the very center, stars follow more familiar routines. The spiral arms of a galaxy, those grand cosmic wheels, drift and whirl as if drawn by the gravitational tides. Each arm, each cluster, is part of the ballet, moving under the combined pull of all matter, dark and bright. The black hole's role here is small, but not negligible. It keeps the inner disk tight and uniform, preventing chaos that might otherwise break the pattern. In many galaxies, a bar of stars spans across the core like an elongated wheel. Some studies hint that a black hole's presence can influence these bars, perhaps by resonantly aligning certain orbits. It's as if the bar responds to the central weight, aligning itself to a resonant frequency set by the black hole's gravity. The result is a graceful structure, its design echoing the unseen mass at the center. Galactic bulges in spirals and elliptical galaxies are also shaped by their unseen anchor. In elliptical galaxies, stars swirl in 3 dimensions, like a flock of birds in a globular dance. Even there, the black hole sits at the heart, nudging the nearest stars into tighter loops. Though more chaotic, this galactic crowd still moves around its center, where the black hole silently reigns. Galactic collisions can leave behind wandering dancers. When a smaller galaxy is absorbed, its own black hole may not merge right away. It might sling into a wide orbit around the main galaxy, dancing far from the center. Scientists predict that galaxies like the Milky Way could harbor such rogue black holes from past mergers. They would quietly orbit unseen, adding complexity to the choreography of stars in the halo. One final note. The stars themselves sometimes carry scars of the dance. Close encounters with the black hole can change their orbits or even tear stars apart, as we have seen. Occasionally, a star will gain such speed that it flies out of the galaxy entirely, becoming a wanderer. These hypervelocity stars are like a break in the music, a sudden burst, leaving the dance floor forever. Even our own solar system is part of this grand dance, though we are far from the center. We orbit the galaxy at a gentle pace, taking about 230 million years to circle once. This is a slow waltz compared to the frenetic dances near the core. Still, the black hole at our center is the conductor of the galaxy's grand performance, even if we only feel a slight tug from afar. Every star in the sky is a dancer tracing a path in the gravitational ballet. Together, they form the living tapestry of the galaxy, and at the center, the black hole is the unseen choreographer. Through cosmic eons, stars will continue to dance, black holes will merge, and new patterns will emerge. We are privileged to witness just a moment of this dance, and much remains to be seen. After the feast and the dance comes the aftermath. Black holes can breathe out powerful winds that change their galaxies forever. These are the winds of change, streams of particles and energy flowing outward from the galactic center. The black hole seems to sigh or roar, and in that breath it can sweep away the very materials that once fed its feast. What remains is a galaxy forever altered by its giant's exhalation. To form stars, a galaxy needs cold gas. But a hungry black hole's outflows heat and disperse this gas. Instead of collapsing into new suns, the gas is driven outward or heated beyond cooling. It is as if the black hole's winds clear away the garden's soil, just as new flowers were about to bloom. In effect, the black hole shuts down star formation in the galaxy. Astronomers have seen this destructive wind in action. For instance, in a galaxy about 2.3 billion light-years away, telescopes detected a fierce wind from the black hole that was blowing star-forming clouds away. Cold clouds that might have become stars were being pushed out into space. This confirmed that a black hole's breath can erase the fuel for future stars, leaving a galaxy sterile. Simulations of galaxy formation confirm these observations. They suggest that when a black hole feeds strongly, only a fraction of its energy acts on the galaxy, but that fraction can be enough to quench star formation. In simpler terms, the black hole may only nudge a small amount of material out, but it's the critical material, the cold gas. Once that is gone, the galaxy goes quiet. Recent studies of young galaxies also found evidence of black hole winds. Telescopes saw neutral hydrogen gas streaming out from galaxies forming a few billion years after the Big Bang. This outflow was so massive and fast that it could remove enough gas to stop stars from forming. It showed that even early in the universe, black holes could abruptly halt galactic growth by a gust of cosmic wind. These winds have dramatic consequences. Galaxies with strong winds often end up in a quiescent state, no longer birthing stars. Their colours redden as old stars age without replacement, and they join the ranks of red and dead galaxies. Over time, the wind's touch can transform a spiral of young blue stars into a dusty, dim spheroid of aging giants. These winds can reach staggering speeds. Observations have found outflows travelling at millions of miles per hour, fast enough to fling gas into intergalactic space. Some flows are visible in ionized gas, others in cold molecular gas. In total, these outflows can carry away the fuel that stars need, enough to significantly change a galaxy in a short time. Astronomers have also identified X-ray cavities and radio lobes that are relics of black hole activity. These look like bubbles blown into the galaxy's halo, carved by past jets and winds. For example, the galaxy M87 has giant radio lobes, showing where its black hole once inflated balloons of hot gas. In cluster cores, ripples in the hot gas reveal sound waves from ancient black hole outbursts. These structures indicate that the black hole's winds and jets have been shaping their surroundings for eons. Our own Milky Way may have once felt such winds. The Fermi bubbles, those giant gamma-ray lobes arching above the galactic plane, are thought to be fossils of past outbursts from the central black hole. They show that even here, the black hole once blew a cosmic gale that puffed bubbles into the halo. In the grand scheme, every galaxy with a black hole likely experiences such cleaning winds at some point. Galaxies often live through cycles. A windswept galaxy may sit quiet for a while, and over time cold gas can cool and rain back in. If enough new fuel collects, the black hole may feast again, reigniting bright activity. Then once more it may expel the gas. Through countless such seasons of feast and famine, a galaxy's history is written. The black hole's silent bluster is not a one-time event, but part of a continuing saga of creation and change. These winds of change remind us how dynamic galaxies are. The narrative of a galaxy's life includes silent gusts and storms from its heart. But our story is far from over. The galaxy will continue to evolve under the watchful eyes of its sentinel at the center. The journey into the galactic heart goes on. Far beyond the reach of any human eye, black holes hide in the cosmic night. They emit no light of their own, cloaking themselves in perfect darkness. Yet across the quiet expanse of space, these enigmatic giants cannot remain entirely hidden. The universe has its ways of revealing even the most secretive of its objects. To find something so dark and silent, we must listen for its subtle whispers and search for the faint glimmers it stirs around itself. In the vacuum of space, sound cannot carry. No air means no audible noise as stars orbit or as galaxies collide. But there is another kind of sound, a soundless music that travels through the fabric of space-time itself. This is gravity's song, the rippling chorus of gravitational waves. When massive bodies like black holes move and merge, they send faint tremors through space and time, like a stone dropped in a still pond, sending ripples across water. For more than a century, this music played utterly beyond our hearing, a silent symphony unfolding in the darkness. Now, at last, we have built instruments that allow us to listen to the cosmos in this new way. Deep in isolated laboratories on Earth, long tunnels armed with lasers sit in eerie stillness, waiting for a signal. These gravitational wave observatories are like giant ears pressed to the fabric of the universe, listening for any slight distortion. When a gravitational wave passes through our planet, it stretches and squeezes space by a tiny amount. far too small for any human to notice. But within these detectors, laser beams flying back and forth down vacuum tunnels can sense a shift as small as a fraction of a proton's width. It is a feat of patience and precision. The instruments must remain undisturbed by even the faintest tremor, the rustle of wind, or the rumble of distant traffic. They wait in quiet vigil for the rare moments when the universe itself shivers. For years, they heard nothing but the soft hum of earthly noise. Then, one day, the silence was broken. A delicate vibration, almost unimaginable in its subtlety, reached our detectors. It arrived first at an observatory in Louisiana, then, just 7 milliseconds later, at another in Washington state. This minuscule delay told us that a gravitational wave had swept through Earth, coming from the distant southern sky. Buried in that whisper was a story. 2 black holes, locked in a spiraling embrace, were merging over 1 billion light-years away. At first, the wave was so gentle that it barely tickled the instruments. But as the black holes drew closer together, circling faster and faster, the wave's pitch rose in a rapid climb. In the final fraction of a second, the 2 black holes collided and coalesced into one larger black hole. The fabric of spacetime rang like a bell. Our detectors caught the brief crescendo, a rising chirp that lasted only a heartbeat and then abruptly cut off. That faint chirp was the farewell of 2 black holes becoming one. Scientists around the world recognized it instantly. We had just heard the universe speak in gravity's voice for the very first time. It was a profoundly gentle sound by the time it reached us. Yet it arose from one of the most violent events in the cosmos. In that distant collision, 2 immense black holes, each dozens of times the mass of our sun, had circled each other for eons. In an instant, about 3 suns' worth of mass was transformed into pure energy, released as gravitational waves. For a brief moment, that merging black hole outshone the entire visible universe in power. And yet, by the time those ripples travelled across 1 billion light-years to reach Earth, they had stretched our detectors by less than a fraction of an atom's width. It's as if the cosmos screamed, but from so far away that we caught only a whisper. This detection confirmed a long-held prediction of general relativity. Gravitational waves were real, and we could feel them. More than that, we could listen to black holes in a way no telescope could manage. Before this, black holes merging in darkness would have been completely invisible to us. They produce no light when they collide, only bursts of gravitational energy. In cosmic collisions involving other objects, like neutron stars, there can be light and high-energy radiation alongside the gravitational waves. Astronomers once observed 2 neutron stars merge, and telescopes caught a flash of gamma rays along with the glow of heavy elements forged in the crash. But when 2 black holes collide, there is no light at all, no fireworks to announce it. Only the ripple in space-time carries news of that dark event. Now, armed with this new sense, we could finally witness these hidden dramas of the universe. It was as though we had gained an extra sense, an ear tuned to the cosmos, to perceive what was once undetectable. After that first historic whisper, many more followed. Our gravitational ears grew sharper as the detectors were refined and new observatories joined the listening network. We began to pick up the steady rhythm of the universe, dozens of black hole mergers, each with its own faint song. Some chirps were high and quick, from smaller black holes coming together. Others were low and drawn out, from more massive pairs. Each signal marked the final dance of 2 black holes, unseen by any eye, yet briefly singing out in gravitational harmony. In the years following the first detection, our cosmic eavesdropping grew ever more fruitful. What was once a solitary chirp became a chorus, as dozens of black hole mergers were heard by our observatories. With each observing run of the gravitational wave detectors, new signals arrived from different corners of the universe. These discoveries revealed black holes of types we had never recorded before. Some were far heavier than any stellar black hole known from X-ray studies, forcing scientists to reconsider how such massive stars could form and collapse. Black holes of 30, 40, even 50 times the Sun's mass crashed into one another, suggesting that successive mergers might have built up these heavyweights. In one case, we even heard the telltale song of a black hole merging with a neutron star, a lighter, dead star made of crushed atomic matter. That collision produced gravitational waves and, astronomers believe, a faint burst of gamma rays as the neutron star was torn apart, giving us a sneak peek at how multi-messenger astronomy might unfold for these extreme events. It is astounding to think that what was once entirely theoretical, black holes dancing in the dark, is now something we can observe almost routinely. The universe is full of these silent mergers, and at last we have the instruments to listen in on them. With each new detection, we learned more about these mysterious objects. From the precise tone of the waves, scientists could tell how massive the black holes were, and even how fast they spun around each other in their final moments. We heard black holes 10 times the mass of our Sun, and others 50 times or more. In one extraordinary case, we caught the merger of two black holes so hefty that their union created an entirely new giant, a black hole over 100 times the Sun's mass. It was the birth of an intermediate mass black hole, witnessed through the subtle tremor it sent through spacetime. Each gravitational wave signal is fleeting, lasting only a second or two, but its implications echo for much longer. We can replay these signals by converting them into sound. What was once just a squiggly line on a graph becomes a faint chirp or a gentle thump in the quiet of a lab. Listening to these recordings, we can close our eyes and imagine two invisible titans merging in a far-off void. The experience is haunting and humbling, a quiet cosmic lullaby carrying news of an unfathomably distant cataclysm. Our gravitational listening has grown even more ambitious. Not satisfied with hearing only the short chirps of stellar mass black holes, scientists are reaching for the slow, deep hum of far larger ones. When galaxies collide and their supermassive black holes, millions or billions of times the Sun's mass, orbit each other, they too send out gravitational waves. These waves undulate far more slowly, swelling and receding over months or years, like a deep note held on a cosmic organ. No instrument on Earth is large enough to detect those directly. However, plans are already underway to extend our ears into space. One day, an observatory made of spacecraft separated by millions of kilometers will listen for these stately waves from orbit, capturing the cosmic bass notes of merging galaxies. For now, astronomers have turned to a clever alternative. They have transformed entire galaxies into tools for detection. Distant pulsars, spinning neutron stars that blink radio waves in a steady beat, serve as precise ticking clocks scattered across the sky. As gravitational waves from dancing supermassive black holes ripple through space, they imperceptibly alter the timing of those pulses. By comparing the beats from dozens of pulsars over years, scientists can discern the faint background chorus of gravitational waves reverberating through the cosmos. Indeed, hints of this gravitational wave background have now been detected. It's as if beneath the individual chirps of merging stellar black holes, we have begun to hear a constant, bass-like hum resonating throughout the universe. This gentle rumble likely arises from the collective murmurs of countless supermassive black hole pairs slowly spiraling over cosmic history. A deep, cosmic chorus humming in unison across the ages. The very fact we can detect this hum is astonishing. It required turning our galaxy into an enormous observatory and listening with exquisite patience to the quiet tremble of spacetime. From the delicate ringing of laser beams in a silent laboratory to the grand timing of pulsars spread across the Milky Way, gravitational wave astronomy has opened a new realm of perception. It is a silent sense in many ways, one that demands immense stillness and precision, but its revelations are profound. Through it, black holes that were once silent and invisible have found a way to speak. We have begun to hear the life stories of black holes, how they meet, dance, and eventually merge. Each signal is like a greeting from 1 billion years in the past, an echo of a moment when gravity reigned supreme and two black holes became one. Listening to gravity's song has transformed our understanding, but it is only one way to find a black hole. Even as we continue to refine our cosmic hearing, we also use our eyes, telescopes attuned to every kind of light, to seek the faint glow that reveals a black hole's presence. Most black holes do not announce themselves with dramatic collisions. Many lurk quietly in darkness, betrayed only by their subtle effects on nearby matter. And so, we turn from the realm of sound to the realm of light, to discover how black holes illuminate the darkness around them. For all their darkness, black holes often announce themselves through the light they inspire. When matter drifts too close to a black hole, it doesn't disappear silently. Instead, it swirls into a disk around the black hole, whipping around like water circling a drain. Friction and compression heat this infalling gas to extraordinary temperatures. In that intense embrace, the gas glows brilliantly, often in X-rays and other energetic forms of light, invisible to our eyes, but detectable with specialized telescopes. Thus, the very act of being pulled into oblivion can create a beacon, a radiant halo heralding the presence of a black hole deep inside. Over half a century ago, astronomers began to discover such beacons. In the 1960s, detectors lofted above Earth's atmosphere picked up mysterious flashes of X-rays coming from space. One particularly bright and flickering source was found in the constellation Cygnus, the Swan. It defied easy explanation. Here was an object far outshining the sun in X-ray light, yet no bright star was visible at that position. As astronomers studied this source, later named Cygnus X1, they uncovered an intriguing scenario. A normal blue supergiant star in that region seemed to be orbiting an invisible partner, a massive star swaying under the gravitational pull of something unseen. Calculations showed that the hidden object tugging on the star was too massive and too compact to be a normal star, or even a neutron star. The only plausible explanation was a black hole, siphoning gas from its bright companion and heating that gas until it glowed in X-rays. Cygnus X1 thus became one of the first strong black hole candidates, a cosmic X-ray lighthouse powered by a hungry, invisible maw. Since then, many similar X-ray sources have been found in our galaxy and beyond. These systems typically consist of a stellar mass black hole and a normal star locked in close orbit. Gas from the star spills toward the black hole, collecting in a swirling accretion disk. As the gas spirals inward, it heats up to millions of degrees, unleashing floods of X-rays and sometimes gamma rays. From Earth, we observe these systems as flickering X-ray lights in the night, the dying glow of matter as it is consumed. By studying the patterns of these X-ray flickers and the specific energies of the light, astronomers can infer the properties of the unseen black holes, their masses, their spins, and how quickly they are gobbling up matter from their companion stars. In fact, by examining the exact color signatures of X-rays from gas near a black hole, astronomers have seen remarkable distortions caused by gravity and motion. For example, an X-ray emission line from iron atoms in the accretion disk might appear stretched and skewed. This is because one side of the disk is coming toward us at a fraction of light speed, making the light slightly bluer, while the other side is receding, making it redder. And all of the light is also dragged to lower energy by the intense gravity. The result is a broadened, skewed spectral line, a sort of fingerprint of Einstein's physics at work. By fitting these fingerprints with theoretical models, scientists can estimate how fast the inner disk is orbiting and thus infer the black hole's spin. In this way, incredibly, we have measured the spins of black holes light years away, purely by the telltale quirks of the light that escapes from just outside their horizons. Not all black holes dine gently. Sometimes a black hole devours matter too quickly, leading to chaotic eruptions of light. The accretion disk can become unstable and suddenly hurl out jets of particles, or a rapid influx of gas can trigger powerful X-ray flares. In some systems, astronomers observe dramatic swings in brightness, as if the black hole's meal periodically flares up in a sudden blaze before settling back down. Such outbursts, while tumultuous, also shed light on the black hole's immediate surroundings. They reveal a dynamic dance between gravity and radiation just outside the event horizon. Even in the violence, there are clues. The particular energies of the X-rays emitted and the speed of their flickering tell us how close to the black hole's edge these eruptions are taking place. It is remarkable that by catching these ephemeral flashes from across space, we can map the behavior of matter just a few dozen kilometers from a black hole's maw. While stellar mass black holes announce their presence through these X-ray fireworks, even mightier beacons shine from the hearts of distant galaxies. In the 1960s, radio telescopes and early optical surveys revealed quasars, objects that appeared star-like, yet poured out more energy than entire galaxies. These enigmatic lights baffled astronomers. What could possibly power such brilliance at a galaxy's core? The answer, realized over time, was a supermassive black hole gorging itself on infalling gas. Gas and dust funnel into the galactic center, forming a colossal accretion disk around the giant black hole. As matter piles up and swirls inward, the inner regions of the disk heat to tens of millions of degrees, glowing fiercely across the electromagnetic spectrum. A quasar is the result, the heart of a young galaxy blazing with the light of trillions of suns, powered by a cosmic engine no larger than our solar system. These actively feeding supermassive black holes, often called active galactic nuclei, are among the brightest objects in existence. Ironically, the darkest entities in the universe give rise to the most luminous displays. At their peak, quasars can outshine the billions of stars in their host galaxies, making them visible across immense distances. Some quasars are so distant that their light began its journey when the universe was in its infancy. By observing these brilliant beacons, we are peering deep into cosmic history, witnessing black holes that were already billions of solar masses when the cosmos was young. In this way, light from the abyss serves as a time machine as well as a beacon, illuminating both the black holes and the early era in which they shone. One striking feature of an active galactic black hole is the presence of jets, narrow beams of charged particles flung outward from near the black hole at nearly light speed. Twisted magnetic fields around the spinning disk and black hole focus these jets along the poles of rotation. They pierce through the surrounding galaxy, sometimes extending for hundreds of thousands of light years into intergalactic space. These jets glow at many wavelengths: radio waves, visible light, X-rays, even gamma rays. In radio images, they reveal themselves as enormous lobes or plumes billowing from a galaxy's core. Such jets are a clear signature of a feeding black hole, since only a powerful gravitational engine can launch particles with such tremendous energy. When astronomers find a galaxy with giant radio lobes emanating from its center, they know a supermassive black hole resides there, pumping energy into space. One famous example is the giant elliptical galaxy M87. Long before we ever saw the black hole at its center directly, M87's hidden monster announced itself with a spectacular jet. In telescopic images, a bright, narrow filament of light can be seen stabbing out from the galaxy's core, a jet propelled by a black hole billions of times the mass of the Sun. By studying this jet's properties, its brightness, its shape, the incredible speed of particles racing along it, scientists gathered hints of the colossal black hole powering it. The jet was like a cosmic arrow, pointing straight to an otherwise invisible gravitational giant at the galaxy's heart, foreshadowing the direct sight we would later attain. A feeding supermassive black hole doesn't just shine, it can also transform its surroundings. The radiation and winds from the hot accretion disk and the power of its jets can push around the gas in its host galaxy. This process, known as feedback, can heat up gas or blow it out of the galactic core, at times suppressing the formation of new stars. In this way, a black hole, though tiny compared to its galaxy, can influence the galaxy's evolution dramatically. Astronomers see evidence of this in giant bubbles and shockwaves in galaxies, where central black holes have recently had a feeding surge. The black hole at a galaxy's center can act like a furnace in a house, small in size, but capable of warming and stirring the entire environment. This feedback loop between black hole and galaxy is an ongoing area of research, illuminating how intimately connected the fate of a galaxy is to the activities of its central abyss. Yet not all supermassive black holes announce themselves with fireworks. Some lie quiet, like a sleeping dragon in its lair. Our own Milky Way's central black hole, Sagittarius A, is one of these mostly silent sentinels. It is comparatively faint, releasing just a trickle of radiation most of the time. For years, its existence was suggested mainly by a dim radio source, and by the subtle gravitational pull it seemed to exert on nearby stars, rather than by any radiant display. In the 1990s and 2000s, astronomers used powerful telescopes with infrared cameras to peer through interstellar dust and watch the stars near our galaxy's core. What they saw was astonishing. Several stars were whipping around an unseen object at tremendous speeds. One star, now known as S2, swooped incredibly close to the invisible center and then swung far out, completing an entire oval-shaped orbit in just 16 years. At its closest approach, S2 traveled at a few percent of the speed of light, an almost unbelievable velocity for a star. However, the gas around Sagittarius A whips around the black hole in mere minutes. Since the black hole is so much smaller, everything orbits faster, meaning the target's appearance can change even during a single night of observation. It's a bit like trying to photograph a hummingbird flapping its wings. whereas M87's black hole was more like a steady lighthouse turning slowly. The moving stars became messengers, revealing the gravity of the unseen black hole. Watching them loop around the void was like observing leaves swirling around an invisible whirlpool. Their motions exposed the presence of something powerful at the center. Through these patient observations, astronomers essentially saw the black hole's influence. When the results were announced, Sagittarius A transformed from a mysterious radio source into a definitive reality, the dark, central anchor of our galaxy. Humanity had glimpsed the otherwise invisible heart of the Milky Way by tracing the curved paths of stars caught in its grip. Sagittarius A itself occasionally stirs from its slumber, giving off brief flickers of light. X-ray and infrared telescopes have caught sudden flares from our galaxy's center, likely caused by the black hole gulping down a clump of matter. These flares are modest by cosmic standards. They rise and fall within a few hours. But they are dramatic confirmation that the black hole is indeed active at times. In those moments, as we observe a spike of energy from the normally quiet nucleus of our galaxy, we witness a brief feeding episode of our own central black hole. Beyond steady glows and periodic flares, some black hole signals are singular, one-time events. Imagine a lone star wandering too close to a giant black hole in a distant galaxy. The black hole's tidal gravity stretches the star and ultimately rips it apart, shredding it into a stream of gas. This catastrophic disruption, a tidal disruption event, triggers an immense burst of light, briefly rivaling the brightness of a whole galaxy. Over weeks and months, the stellar debris swirls inward and disappears, releasing a brilliant flare that telescopes can pick up billions of light-years away. A flare like this can appear in a patch of sky where no notable light was seen before, shine intensely for a short time, and then gradually fade away. In recent years, astronomers have observed dozens of these stellar tidal disruptions in distant galaxies. Each one is a dramatic showcase of a black hole temporarily revealing itself, turning from quiescence to brilliance as it devours an unlucky star. By analyzing the energy output and how the light dims over time, scientists can estimate the black hole's size and learn about the extreme physics at play as it consumes the star. Though the event is violent, from Earth's perspective, it unfolds almost gently, a slow rise and fall in the night's brightness, whispering the presence of a black hole that we might otherwise never know was there. Black holes can also announce their presence through gravity's subtle lensing of starlight. If a massive compact object drifts in front of a distant star along our line of sight, its gravity can bend and focus the star's light toward us. To an observer, the star briefly appears brighter, as though an unseen lens magnified it. This effect, called gravitational microlensing, has revealed many hidden objects in our galaxy: dim stars, brown dwarfs, even wandering planets. And it can reveal isolated black holes too. In 2022, astronomers reported what is likely the first detection of a solitary black hole using microlensing. For a time, a star in the sky grew unexpectedly brighter and then dimmed again. Detailed analysis showed the light's behavior matched a lensing event caused by an object about 7 times the Sun's mass passing between Earth and the distant star. No light was detected from this intervening object itself. It was completely dark, just as a lone black hole would be. Such discoveries are rare and challenging, but they offer a unique way to spot black holes that roam the galaxy in darkness, far from any star or glowing disk that would give them away. Each of these methods, the X-ray flares of accretion, the radio glows of jets, the dances of stars, the sudden tidal flares, and the bending of light, adds to our growing repertoire of ways to detect black holes. Through decades of patient observation, we have learned to sense the otherwise invisible. We cannot see a black hole directly, but we can see its imprint, the way it makes nearby matter shine, or causes stars to swirl, or even bends the light of background objects. It's akin to identifying an invisible ship by the ripples it leaves and the faint lights it moves in the fog. Bit by bit, these signals have sketched out the once theoretical cosmic giants, the silent gravitational Goliaths at galaxy centers, and the smaller wanderers among the stars are no longer merely dark mysteries. They have become perceptible, even if only indirectly. With ever more sensitive instruments, astronomers continue to seek out black holes, large and small, by these telltale signs. X-ray observatories in space scan for new bursts and flares. Optical and infrared telescopes measure the motions of stars and gas with increasing precision, weighing central black holes and mapping their reach. Radio antennas trace the colossal jets and bubbles blown by feeding black holes. Step by step, the outlines of these invisible objects become sharper in our data, even if no light comes directly from the black holes themselves. And yet, after all this indirect evidence, one question remained. Could we ever truly see a black hole? Not just infer its presence, but somehow capture an image of the darkness itself, the shadow of a black hole's silhouette against the glow of its surroundings. For decades, this idea seemed like fantasy, as black holes are so small and far away. But gradually, technology and perseverance brought this goal within reach. In the next part of our journey, we move from inference to vision, joining the quest to image the unseen and gaze for the first time directly at the face of the abyss. It is one thing to infer a black hole's presence from its effects, and quite another to actually see it. For decades, the very idea of imaging a black hole was considered beyond reach. Black holes are tiny on the sky, even though they are massive. They hide in distant galaxies or shroud themselves behind clouds of dust. Capturing a picture of one would require a telescope of unprecedented power and clarity. Yet, human curiosity was relentless. Astronomers around the world dared to ask, could we one day take a direct image of the unseeable, the shadow of a black hole's event horizon, cast against the glowing material around it? The challenge was immense. The event horizon of a supermassive black hole is minuscule when seen from Earth. To our eyes, even through the best optical telescopes, it would be far too small to distinguish. But there was a clever workaround. Use radio waves and combine many telescopes to simulate one giant telescope as large as the Earth itself. This technique, called very long baseline interferometry, had been used before to sharpen images of distant cosmic objects. Still, applying it to black hole imaging meant pushing technology to its limits. To see detail as fine as a black hole's silhouette in a faraway galaxy, the resolving power needed to be extraordinary, akin to reading a newspaper in New York while sitting at a cafe in Paris. In April of 2017, after years of preparation, a network of radio observatories scattered across the globe all turned to gaze at the same targets. This was the Event Horizon Telescope, a collaboration linking dishes from mountain peaks in Hawaii and Mexico to deserts in Arizona, from high plateaus in the Andes of Chile to the frozen expanses of the South Pole. For several nights, these far-flung antennas acted in unison, synchronized by atomic clocks, collecting whispers of radio waves that had journeyed through space for eons. Among their targets was the gargantuan black hole at the center of the galaxy M87, about 55 million light-years away. Light from that black hole's vicinity had been travelling toward us since the era when Earth's earliest mammals scurried beneath the feet of dinosaurs. Now, at long last, it was being captured on hard drives and tapes at observatories around the world. Each telescope in the network gathered its slice of the incoming radio waves, recording torrents of data. No single observatory could make an image on its own, but together, the subtle interference patterns between their signals held the secrets of an image hidden within. The data were so voluminous that they could not simply be sent over the internet. Instead, they had to be stored on dozens of hard disks and physically shipped to central processing centers. There, supercomputers combined and compared the signals, correcting for the tiniest differences in timing and the blurring effect of Earth's atmosphere at each station. Bit by bit, an image began to emerge, like a faint apparition coming into focus after a long wait. In fact, at the South Pole Observatory, where no flights depart during the long winter, the hard drives filled with data had to wait many months before they could be flown to the processing labs, a final, earthly hurdle in this cosmic imaging quest. 2 years later, in April 2019, the world was shown that image. At first glance, it looked modest, a slightly blurry, ring-like structure, glowing orange against a black background. But this simple picture was the culmination of an astonishing feat of science and engineering. It was immediately recognized for what it was, the silhouette of a supermassive black hole. The picture revealed a bright ring of light surrounding a dark, circular center. That dark center was exactly what theory had predicted. The black hole's shadow, a sort of negative imprint of the event horizon where infalling light vanished from view. We were gazing at the edge of a black hole, the point of no return silhouetted by the glow of hot gas swirling just outside. The ring of light we saw was formed by gas heated to billions of degrees, racing around the black hole under the grip of its gravity. The ring was not perfectly uniform. One side was brighter than the opposite. This too had been expected. The bright side indicated material moving toward us, its light boosted in intensity by its incredible speed, while the dimmer side was gas moving away. It was a stunning confirmation of Einstein's theories. The size of the dark shadow matched closely with calculations based on M87's estimated black hole mass. Nature behaved as the equations of gravity foretold, even in this extreme environment. Yet seeing it with our own eyes, aided by our ingenious instruments, was something profoundly new and stirring. Astronomers and enthusiasts alike reacted with awe. Here, finally, was direct visual evidence of a black hole. It was no longer just an artist's impression or a simulation on a computer screen. It was a real image, obtained by essentially turning our entire planet into a telescope and aiming it at one of the most mysterious objects in the cosmos. In that image, humanity extended its vision to a place where light itself is imprisoned. The sight of the glowing ring and its dark heart had a quiet but powerful effect, a mix of triumph at our technical achievement and a humbling reminder of our smallness before such a mighty void. Further insights came when scientists examined the polarization of the light in the M87 image, the orientation of the radio waves. From this, they mapped the magnetic fields threading through the glowing gas. On the picture of the shadow, they could draw faint lines, showing how magnetic forces swirled around the black hole. These fields likely play a crucial role in launching and shaping the jet that we see shooting from M87. Thus, the first image not only confirmed the black hole's shadow as expected, but also revealed a hint of the unseen structure and forces at work just outside the event horizon. It was striking how closely this image resembled what simulations and even science fiction depictions had long anticipated. Theoretical physicists and artists alike had drawn rings of light encircling darkness. And now, nature herself had painted the same portrait for us. The correspondence between prediction and observation gave us confidence that we truly understand the basic physics of these extreme regions. Not long after the success at M87, the Event Horizon Telescope team turned to a more familiar target, the supermassive black hole at the center of our own Milky Way. Sagittarius A had already been identified through the orbiting stars as a black hole of about 4 million suns, but capturing its image posed special challenges. Sagittarius A is much closer to us, about 27,000 light-years away, than M87's black hole, but it is also over 1,000 times smaller in mass. In apparent size on the sky, it is comparable to M87's giant, which is why the same telescope network can, in principle, image both. However, the gas around Sagittarius A whips around the black hole in mere minutes. Since the black hole is so much smaller, everything orbits faster, meaning the target's appearance can change even during a single night of observation. It's a bit like trying to photograph a hummingbird flapping its wings, whereas M87's black hole was more like a steady lighthouse turning slowly. For our Milky Way's black hole, the data from the telescopes were consequently harder to assemble into a clear picture. The team had to develop new algorithms to account for the rapid variations. After much careful effort combining the observations, they finally unveiled the portrait of Sagittarius A in May 2022. As expected, it showed a family resemblance to the M87 image, a ring of light with a dim center. This one was somewhat blurrier, reflecting the difficulties in capturing a clear snapshot of such a dynamic scene, but it was profoundly meaningful to behold. Our own galaxy's guardian black hole had at last been seen, and it appeared to obey the same physics as its larger cousin. Nature's recipe for a glowing black hole silhouette, it seemed, was universal. The image of Sagittarius A carried a special sentiment. This was the black hole that resides in the center of our galaxy. In a sense, the closest supermassive black hole to us, our galaxy's heart. To have a picture of it made the concept of our galactic center more tangible. It went from an inferred mass hiding behind clouds of dust and stars to something with a visible form, however blurry, that we could look at. In the image, we saw the gentle glow of orbiting gas, a testament to a relatively quiet black hole nibbling on whatever drifts too near. And in the middle, we saw the darkness where the light falls in and does not return. It was both comforting and eerie, like finally meeting an old, legendary character from a story, the monster known to be in the forest, revealed at last, not as a fearsome sight, but as a softly outlined silhouette. These first images of black hole shadows opened a new era of astronomy. They proved that with ingenuity and cooperation on a global scale, we could attain almost absurdly fine detail in our observations, enough to discern the form of an object as elusive as a black hole. But this achievement is not the end of the journey. It is a beginning. With these initial snapshots, scientists have begun to test theories of gravity in ways never before possible. By carefully measuring the size and shape of the M87 black hole's shadow, for instance, they can check whether it matches Einstein's general relativity, or if there are slight deviations that might hint at new physics. So far, Einstein's theory has passed the test, standing firm even at the very rim of a black hole. Future endeavors promise even sharper views and more insights. The Event Horizon Telescope is continually being improved, with more telescopes joining the array and better instruments increasing its sensitivity. Each new station added to the network is like adding a new fragment to a giant mirror, helping to refine the image. Plans are already being discussed to send radio telescopes into space, which could work in tandem with those on the ground to achieve even higher resolution. If realized, such an array might one day image black holes with enough clarity to see the swirl of gas in motion, effectively making a cosmic movie of a black hole's accretion dance. We might witness jets being launched in real time, or watch hotspots of orbiting plasma circling the abyss. For now, we have the monumental first pictures, fuzzy but unmistakable. They have confirmed that what we long imagined is truly there. A black hole, true to its name, does not itself emit light, but we can see the silhouette it imprints on the luminous matter behind it. In a sense, the black hole has become visible through the light it scatters and devours. To look at those images is to gaze at something that was once purely theoretical. It brings a sense of intimate reality to these cosmic phenomena. The orange ring in the image is not merely a simulation or a guess. It's the actual glow from our galaxy's central vortex and from the giant in a distant galaxy. The darkness within that ring is the closest we've come to picturing a hole in space-time itself. As we contemplate those images, taken by our ingenious planet-sized telescope, we can imagine ourselves at the threshold of that dark realm. It is a quiet image, nothing like the explosive vistas of nebulae or galaxies, but one that holds profound weight. It's the still, silent outline of a trapdoor in space and time. In keeping with our gentle journey, the photos of these black holes do not scream with brightness. They glow softly, as if in a gentle twilight, marking the boundary where light succumbs to night. They invite us to reflect on how far our observation techniques have come, from seeing stars wobble, to hearing space-time ring, to finally capturing a direct picture of the cosmic abyss. The story does not end with a static image pinned to a screen. Having seen a black hole, we hunger to understand it more deeply. Each observation we make, in gravitational waves, in X-ray flares, or in a photograph of a shadow, is another piece of the puzzle. And even now, as we marvel at having glimpsed the unseen, we realize that there remain deeper mysteries. The images raise as many questions as they answer. What lies just beyond that veil of darkness? What dances and turbulence occur in the mad whirl of gravity right at the brink? These are questions for the future. Our next steps will involve not just observing with greater clarity, but also listening and feeling for subtler echoes that black holes might emit. With the ability to both hear and see black holes, we have entered a new phase of understanding. The cosmic sentinels at galactic hearts have begun to surrender some of their secrets. Yet, as our view improves, we also become more acutely aware of what we do not yet know. The journey continues, leading us onward into the most cryptic aspects of black hole nature, into the echoes of the unknown that still reverberate beyond our current reach. Even after all these triumphs of observation, profound mysteries remain. Black holes, for all that we can now hear and see of them, still guard the deepest secrets of physics. They are the meeting point of the immense and the infinitesimal, cosmic mass packed into quantum scales. What happens in those extreme conditions? In the silence beyond the event horizon, where our observations cannot reach, questions abound and theories swirl like phantoms. These are the echoes of the unknown, the hints and whispers of truths that have yet to be uncovered. One mystery centers on the ultimate fate of everything a black hole swallows. According to the principles of quantum physics, information, the fundamental fingerprints of matter and energy, should never be destroyed. Yet a black hole seems to erase details with ruthless efficiency. Toss in a chair, a spaceship, or an encyclopedia, and from the outside, all that remains is an incrementally heavier, perhaps faster spinning black hole. The rich details of what fell in appear to vanish. Decades ago, Stephen Hawking put forward a stunning idea. Black holes might slowly evaporate over unfathomable spans of time, emitting a trickle of particle energy now known as Hawking radiation. If so, what becomes of all the information that fell inside? Hawking initially argued that it was gone for good, lost from the universe, erased from existence. This claim sparked a deep paradox and a debate that has raged in theoretical physics ever since. Imagine a black hole, completely dark, except for a faint glow at its edge, as it very slowly radiates away energy. This glow is Hawking radiation, a quantum whisper from just outside the event horizon. For a stellar mass black hole, this whisper is utterly negligible. It would take trillions upon trillions of years for such a black hole to evaporate. No telescope could hope to detect it directly. Given enough time, they leak. This leakage presents a dilemma. Does the Hawking radiation carry away the information of what fell in some coded form? Or is the information truly lost, violating a core tenet of quantum theory? Hawking's own calculations suggested information was lost, a conclusion that unsettled many physicists. Over the years, opinions shifted. Most now suspect that somehow, in ways not yet fully understood, the information does find its way out, perhaps encoded in subtle correlations within the radiation. How that message might be encoded is unknown, and discovering the answer will likely require a breakthrough in our understanding, a unification of gravity with quantum mechanics. The surface of a black hole's event horizon, some suggest, could behave like a giant hologram, storing the information of everything that passes through it. In this holographic theory, the three-dimensional information of objects that fall in might be preserved on the two-dimensional boundary, much as a hologram can encode a 3D image on a flat film. Under this view, the black hole's final whisper would not be just random heat, but a kind of encrypted message of everything it ever consumed. But no one knows for sure if this is how nature works. Black holes have become testing grounds for ideas at the cutting edge of physics, ideas that tie together quantum theory, information science, and the geometry of spacetime. Another riddle is what happens deep inside a black hole. At the center, our equations predict a singularity, a point of infinite density and zero volume, where space and time as we know them come to an end. Of course, infinite density is likely a sign that our current theories have hit their limit. Somewhere beyond our reach, new physics must take over. Perhaps quantum effects create a new state of matter, or space-time undergoes a metamorphosis we can't yet imagine. Some scientists speculate that the singularity might not even be a point at all. It could be spread out by quantum uncertainty or replaced by a core of exotic, quantum-corrected space. There are even fanciful musings about whether the matter that falls in might rebound into another place or universe entirely, turning the black hole into a bridge or a one-way door, often called a wormhole or a white hole in science fiction. These ideas remain speculative, with no evidence that our universe's black holes actually behave this way. But they serve to remind us how little we truly grasp about gravity at its most extreme. When two black holes collide and merge, as we have observed through gravitational waves, the merged black hole rings like a struck bell. In the final wave signals of such events, physicists have searched for something unexpected, slight anomalies or echoes that could hint that the event horizon is not the hard cutoff classical theory says it is. If a black hole's event horizon were instead replaced by some strange quantum boundary, the gravitational waves might bounce and reverberate, producing additional faint chirps after the main merger signal. So far, our detectors have not definitively heard these speculative echoes, and standard general relativity has held up exceedingly well. But the fact that we can even listen for them is a testament to how far our observational powers have come. With each new generation of instruments, we test black holes, not just as astrophysical objects, but as laboratories of fundamental physics. Each observation is an opportunity to catch a whisper of new physics in the roar of the well-understood. There are other puzzles too. We still don't fully know how the earliest supermassive black holes formed so quickly in the young universe. Some were already billions of solar masses when the cosmos was only a few 100 million years old. Did they grow from the seeds of collapsing primordial stars? Did they form from direct collapses of vast gas clouds, or even from dense clumps of dark matter? These questions are under intense investigation. The echoes of those ancient times might be found by new telescopes that peer back to the dawn of galaxies, searching for infant quasars and unusual radiation that could signal nascent black holes. Every faint glimmer from the distant past is like an echo carrying information about how these cosmic giants came to be. We also are not sure how many intermediate mass black holes roam the cosmos, filling the gap between stellar and supermassive. We have caught hints. The gravitational waves from a merger that produced a black hole of about 150 solar masses, for example, gave us the first confirmed intermediate mass black hole. And there have been X-ray and dynamical clues of others in star clusters or dwarf galaxies. But these mid-sized black holes remain elusive, hidden in shadows. Finding more of them would complete the picture of black hole evolution, showing us how black holes grow and merge through cosmic time. Are they stepping stones that link the tiny and the titanic? Or are supermassive black holes born and grown by entirely different means? The universe has yet to fully reveal that story. Each mystery we've mentioned is like an unanswered call in the dark, an echo waiting for a reply. As our tools and techniques improve, we might one day detect the almost silent whisper of Hawking radiation or decipher subtle patterns in gravitational wave signals. We might capture high-resolution movies of matter dancing madly around black holes, watching for deviations that betray new physics. We could discover black holes of unexpected mass or origin that challenge our theories of formation. And we will continue to listen across the spectrum, from radio waves to gamma rays, and in gravitational waves and neutrinos, for any message these dark objects send us. Multi-messenger astronomy, the combined use of light, particles, and gravitational waves, stands at the frontier of this quest. A shining example occurred in 2017, when a collision of neutron stars was observed in gravitational waves and across the electromagnetic spectrum, yielding a treasure trove of insights. For black holes, a similar multi-messenger moment is harder to come by, since black hole mergers give off no light. But we have already paired gravitational wave detections with searches for light in cases like a black hole merging with a neutron star. In one instance, gravitational waves announced such a merger, and telescopes were alerted to look for any afterglow. A faint gamma-ray burst may have been seen. In the future, as detectors become more sensitive, we might catch a black hole merger happening in a messy environment filled with gas or a star, producing a flash that telescopes can see. That would be an extraordinary event. Hearing the space-time quake of a black hole collision, and simultaneously seeing a burst of light from the dying moments of matter being consumed. It would be as if the universe briefly allowed us both sight and sound of a usually hidden drama. Even neutrinos, nearly massless particles that rarely interact with matter, have been enlisted in our study of black holes. In 2018, a high-energy neutrino was detected on Earth and traced back to a distant Blazer galaxy, a galaxy with a jet powered by a supermassive black hole. This single neutrino, a tiny particle flying solo across intergalactic space, was likely born in the vicinity of a black hole's ferocious jet. It's a bit like catching a lone spark from a far-off fireworks show. It tells us something astonishing took place and connects that event to the black hole's central engine. In the coming years, neutrino observatories may detect more such particles, giving us yet another way to probe the environments around black holes. Through all these methods, we are gathering pieces of a puzzle that is as vast as it is deep. Each gravitational wave, each photon of light, each neutrino or cosmic ray that reaches us from a black hole is a messenger carrying information. We have learned to receive these messages with increasing clarity. And as we assemble them, the once abstract notion of a black hole is gradually taking on a more comprehensible form. We may not be able to visit these enigmas directly, but we are feeling out their contours through the vibrations and light they send forth. Yet, even as the image sharpens, the ultimate truth remains veiled. Black holes still stand as portals to the unknown in a figurative sense. Not gateways for travelers, perhaps, but gateways for knowledge, leading us to realms where our current theories falter. To solve the riddles they pose, we may need a new kind of physics that perhaps only future generations will fully develop. It is humbling to know that, for all our progress, we are still scratching at the surface of a great mystery. Our journey thus far has taken us from the first inklings of black holes' existence to actually capturing their image and listening to their symphonies. We have peered at the sky with every tool at our disposal and transformed our planet into a giant observatory, all to understand these cosmic paradoxes. And with each answer we've gained, new questions echo back. This story is far from over. The path ahead leads deeper, toward the very edges of knowledge where black holes reside. In time, and with much patience, we will continue to chip away at these enigmas. What we find may not only illuminate black holes themselves, but also fundamentally reshape how we view space, time, and the nature of reality. Gently, the narrative of discovery urges us onward. In the quiet of midnight laboratories and the stillness of remote observatories, we will keep listening, keep watching, and keep wondering. The Sentinels of the galactic deep have more to tell. Their voices, in gravity's waves, in ghostly particles, in subtle shifts of starlight, call out to us, inviting us to solve the next puzzle. And as we follow those faint echoes into the unknown, we remain wrapped in a sense of calm and awe, comforted by the knowledge that even in darkness and mystery, the universe speaks, and we are learning how to listen. Our exploration continues, ever deeper, ever more quietly profound. The final part of our journey awaits, where we will reflect on all that these cosmic sentinels have taught us, and what they mean for our understanding of the universe. The cosmic night is vast and full of stories, and the tale of the black holes is still unfolding, softly guiding us toward the horizon of new discovery. In the earliest moments after creation, the universe was a silent expanse of darkness. No stars or galaxies had yet flickered into life. At that time, space was calm, but full of potential. Invisible forces and subtle fluctuations lined the cosmic fabric like ripples on still water. In that quiet place, the seeds of future giants were planted without making a sound. For some time, physicists have even whispered of primordial black holes, cosmic relics formed in the very birth of the universe. They imagine that when space itself trembled into existence, small regions could collapse into black holes. These primordial seeds would be born in the densest knots of the cosmic fabric. Hidden from any light, they would be silent guardians of darkness, present from the first heartbeat of the cosmos. Over eons, such seeds could slowly grow, quietly tracing the universe's earliest memories. For hundreds of millions of years after the Big Bang, the universe remained a dark place. Only faint signals like the cosmic microwave background escaped the silence. Then, finally, the first stars, gigantic, brilliant, metal-free giants, ignited in the darkness, signaling the end of the cosmic night and the dawn of a new era. Their ultraviolet light began to heat and rayonize the gas around them, paving the way for the formation of galaxies. In reality, the earliest black holes may have had a humbler origin. In the first few 100 million years, the cosmos began to kindle light as massive new stars ignited. These first stars, often titanic and ephemeral, burned their fuel quickly and ended their lives in powerful explosions. When a giant star blew apart in a supernova, its remaining core could collapse into a black hole. Thus, the first stellar mass black holes were born, seeds only tens of times more massive than our Sun, yet destined to grow in the dark. So the cosmic cradle gave birth to a new darkness, though relatively small at first. These juvenile black holes were mere infants on the cosmic timeline and would need to grow. If conditions allowed, they could feed on surrounding clouds of gas and dust, devouring it like cosmic predators. They could also merge with neighboring black holes, doubling their weight like children teaming up. Yet even with these habits, a mystery remained. When astronomers look back to the universe's youth, they find monsters so enormous that feeding alone seems insufficient. Some supermassive black holes observed in the early universe are far larger than simple growth from small seeds could explain. To explain these cosmic puzzles, theorists have proposed a bolder idea: heavy seeds of darkness. In some rare corners of the early universe, colossal clouds of primordial gas could have collapsed directly, without first fragmenting into stars. In a dramatic collapse, the cloud would not create stars at all, but instead plunge straight into a black hole. This direct collapse black hole would already be thousands, or even tens of thousands of times the mass of the Sun upon birth. Massive infants, almost fully grown at the moment of creation. Such heavyweight seeds would give the resulting giants a monumental head start, sidestepping the slow process of growing from small fry. Though born of darkness, these seeds set the stage for an epic cosmic drama. Over the eons, they would gather matter relentlessly, feeding on interstellar gas and dust, merging with other black holes, and growing ever heavier. Slowly and quietly, these seeds of darkness began to carve their influence on the ancient universe. As the galaxies around them became more structured, the black hole seeds matured. The stage was now set for new wonders. The birth of truly colossal black holes, cosmic titans that would come to rule the hearts of galaxies. In the calm aftermath of creation, these fledgling black holes found themselves surrounded by a growing cosmic nursery. The first galaxies began to assemble from vast, swirling clouds of gas, under the gentle pull of gravity. Slowly, these clouds flattened into spinning disks and spun into clusters of new stars. Amidst this budding ecosystem, each central black hole lay at the heart of a galaxy, encircled by enormous reservoirs of gas and dust. Here, in these cosmic cradles, the seeds of darkness would feast and grow, marking the true birth of future giants. Surrounded by the swirling mass of nascent galaxies, a hungry black hole could gorge on gas and dust. As this matter spiraled in under immense gravity, it formed a whirling accretion disk around the black hole. Friction and heat in the disk made it glow brilliantly across the spectrum, from visible light to X-rays. To a distant observer, these luminous disks heralded the presence of quasars, cosmic beacons blazing at the dawn of time. In these quasars, black holes had become ferocious predators of their galactic environment, growing at astonishing rates and outshining whole galaxies in the process. These voracious black holes unleashed prodigious amounts of energy. They launched twin jets of high-speed particles that pierced through the surrounding galaxy and sent out powerful beams of radio and X-ray radiation. Yet, for all this fury and flash, there was an odd serenity in the grand cosmic ballet. The universe's evolution pressed onward at its own pace. The cosmic symphony continued its slow, graceful dance, even as these titans blazed. With an almost majestic patience, these seeds continued to accumulate mass. Hundreds of millions of years passed, and still the pattern held. One black hole grew to the mass of 1,000,000 suns, another to 100 million. Across the cosmos, quasars glowed brightly at dawn, each one telling a story of a ravenous black hole devouring its galactic meal. They were the lighthouses of a young universe, each blazing with the hunger of a voracious heart at the galaxy's center. As a black hole's accretion disk shone brightly, it also regulated the feeding process. Intense radiation pressure could drive away infalling gas, limiting how fast the black hole could grow. Yet black holes found ways to overcome these limits. Under the right conditions, gas could funnel in through thick clouds or bursts, allowing a black hole to consume material at a supercharged rate. This fierce hunger transformed the black holes into cosmic dynamos, converting even a fraction of the swallowed mass into powerful light. For every giant black hole, there were cosmic rivers feeding them. Vast filaments of gas stretched between galaxies, continuously supplying material. The cosmic web funneled hydrogen into the heart of clusters and galaxies, like lifelines feeding these hungry beasts. This gas flow allowed young black holes to feast and grow, even when stars might have depleted local fuel. Not all cosmic giants were active at once. Some black holes lay dormant for eons, quietly lurking until a fresh supply of gas woke them up. Others blazed brilliantly in their younger years. Each black hole's history was unique, sometimes flickering on and off as it swallowed or was starved of fuel. As these giants feasted and spun their vast webs, their host galaxies also changed. The gravity of the growing black hole helped to organize stars and gas in the galactic core. Gas, funneled inward, could trigger new star formation or be heated and ejected by the black hole's energy. In this feedback loop, the fates of galaxies and their central black holes became intertwined in a grand cosmic harmony. And as these giants feasted and spun their vast webs, something remarkable happened. The very fabric of the universe began to ripple. Every massive event, every gobbling of gas, every clash of stars, every merging of black holes, sent gentle undulations through spacetime. Like stones dropping into a cosmic pond, the grand mergers of darkness created faint but detectable tremors. In time, these ripples would be heard as whispers from the deepest places of the cosmos, evidence of titanic collisions that shaped galaxies far and near. Across the vast cosmic expanse, galaxies continued to grow and evolve around their feeding black holes. Over time, it became inevitable that galaxies would encounter one another in slow, majestic dances governed by gravity. Massive galaxies were drawn together by their mutual pull, and with them came their central black holes. When two galaxies began to merge, their black holes embarked on a dramatic chase. Each black hole circled the other in a tightening spiral, like twin dancers locked in a final waltz. Slowly but surely, these titans would come together and unite into a single, colossal power at the heart of the merged galaxy. In the newly merged galaxies, two black holes now lurked at the core, locked in a tight orbit. They circled each other at incredible speeds, moving ever closer with each revolution. This cosmic dance was both violent and beautiful, stretching and warping the very fabric of space and time around them. Finally, in a moment of cosmic significance, they merged in an explosive union. Two became one, forming a single, more massive black hole. In that instant, space-time rippled outward with the energy of the collision. With such collisions, something magical happened far away. The violent union unleashed a powerful burst of gravitational waves, ripples that radiated outward from the merging black holes in every direction. Though these waves are utterly invisible and insensible to our direct senses, they carry with them the story of the Titan's final embrace across the universe. They are, in a sense, echoes of both destruction and creation, vibrations in the very fabric of existence, spun off from the cosmic collision. On our own Earth, scientists have learned to tune in and listen for these cosmic shimmers. In 2015, the LIGO Observatory first detected the faint quiver of space-time from the merger of two stellar mass black holes. Those were small compared to the titanic collisions we have been describing, yet they proved that gravitational waves could indeed be heard. Since then, even more massive pairs have been heard merging, including black holes heavier than any that standard models had imagined. Each detection reverberated like a new clue, confirming that black hole collisions send faint whispers across the universe, carrying secrets from billions of years ago. Looking ahead, future instruments, such as the LISA Space Observatory, will one day eavesdrop on even grander collisions. The merging of truly enormous, supermassive black holes in distant galaxies. For now, an ensemble of cosmic timers is already at work. Pulsars, those precise, ticking remnants of dead stars, are used like a galactic-scale gravitational wave detector. By monitoring the arrival times of pulses from many pulsars across the sky, scientists have started to hear a gentle, persistent background hum in space-time. This subtle background is like the collective echo of countless black hole mergers over cosmic history, a faint symphony composed by the collisions of ancient titans. Sometimes, a merging system could include more than two black holes. If three galaxies collided in sequence, their three central black holes might engage in a chaotic dance. Gravitational slingshots could then fling one of the black holes out of the core at high speed, sending it wandering through space as a rogue. The remaining pair would still spiral and merge, while the castaway black hole became a solitary wanderer in the void. When black holes merge, the final object can receive a powerful recoil, a kick from asymmetrical gravitational wave emission. If the newborn black hole is thrown at high speed, it might wander away from the galactic center. In rare cases, it could even escape its galaxy entirely, a wayward giant drifting in intergalactic space. Detecting such rogue black holes would be a proof of the violent physics at play in these cosmic dances. In the quiet halls of observatories and in laboratories around the world, scientists dream of hearing those echoes from our cosmic past. We imagine standing in a calm room, instruments capturing the final ripple of a merging black hole pair in a faraway galaxy, an event that actually occurred billions of years ago. While such moments are still rare, every bit of data counts. Each gravitational wave we detect, each pulsar's steady rhythm we measure, adds one more note to the grand story of colliding titans. Piece by piece, we assemble the narrative of these ancient cosmic dances. After the tumult of creation and the feast of galactic growth, a vast quiet persisted. In that tranquility, a faint glow lingered on. Everywhere the universe held its memories, etched into the fabric of space-time and light itself. Both photons and gravity bore witness to those primeval events. The echoes of ancient black hole mergers, though subtle and faint, stretched across the cosmos. Slowly, we have begun to discern these whispers in the dark, listening to the earliest chapters of the universe's life. For example, astronomers have discovered a faint, steady hum in space-time by watching a network of pulsars across our galaxy. These pulsars, the spinning remnants of dead stars, serve as precise clocks in the sky. Tiny variations in their pulse times reveal the subtle ripple of a gravitational wave background. It is as if a distant orchestra is playing an ancient symphony, the collective murmurs of countless black hole collisions from eons ago. In this way, it feels as though the universe has begun to sing its own history, allowing us to decode the long-gone dances of black holes that once thumped across the cosmos. These gravitational waves are not the only cosmic echoes. The cosmic microwave background, the faint afterglow of the Big Bang itself, carries stories as well. This ever-present glow bathes the cosmos in ancient light. Within its delicate pattern of fluctuations, scientists search for even subtler signs, minute imprints that could hint at the influence of ancient black holes or their blazing quasars. These might come from the time when the first starlight and black hole radiation began to permeate the dark early cosmos. The cosmic microwave background is like a canvas, capturing the shadows and heat of events long past. Even visible light from distant galaxies is a kind of echo from the past. When our telescopes catch the faint glow of a galaxy's heart, they are seeing black holes and stars as they were billions of years ago. The farther we peer into space, the more our instruments act as time machines. For example, the James Webb Space Telescope recently revealed a galaxy whose light has traveled for nearly 13 billion years to reach us. That galaxy is a snapshot from an era when the universe was still very young, and its black holes were quietly growing in the cosmic dark. Every such observation is a peek through a window in time, an echo of ancient light that tells us how things used to be. Some astrophysicists even speculate that our own existence might somehow be linked to these ancient behemoths. By regulating star formation and distributing heavy elements across galaxies, these old black holes helped shape their host galaxies. The supernovae and energetic jets associated with black hole activity would have sprinkled the raw ingredients for planets and life throughout the cosmos. Though black holes themselves are dark and mysterious, their legacy may be woven into the very fabric of the universe, even into the atoms that make up living beings. In that sense, we might owe a subtle debt to these cosmic architects. Space is suffused with the radiation of countless black holes. X-ray telescopes have mapped an all-sky glow called the cosmic X-ray background, the combined light of millions of unresolved black holes and quasars. Likewise, radio telescopes detect a diffuse hum from ancient jets, and infrared instruments see the heat of dust warmed by early quasars. Each of these backgrounds is like a fossil record, holding clues about populations of black holes that no single telescope could see. By studying these backgrounds, scientists can estimate how many black holes burned fiercely in the past, even if each is too distant or faint to distinguish individually. It's a cosmic census by afterglow, revealing the number of ancient giants that shaped the universe. Gamma-ray telescopes like Fermi have even measured a cosmic gamma-ray background, largely produced by blazars, supermassive black holes shooting jets of high-energy light directly towards us. All these layers of background radiation are like threads in a tapestry, each stitched by the actions of ancient black holes. Even subtle shifts in pulsar timing, slight distortions in the spectrum of light, or minute density fluctuations can all reveal the silent deeds of black holes billions of years in the past. In essence, scientists are using instruments as delicate as cosmic stethoscopes, listening for faint signatures hidden in the vastness of space and time. And so, life on Earth, on a tiny blue dot, is connected by invisible threads to these cosmic giants. Every discovery brings us closer to understanding our place in the grand scheme. The secrets of supermassive black holes are deeply woven into the story of the cosmos, and by extension, into ourselves. Perhaps one day, as we continue to listen and observe, we will clearly hear the next verses of this cosmic saga, chapters that have waited eons to be known. In the silent expanse of the universe, where the light of distant stars still fades into darkness, we find ourselves standing at the edge of understanding. The cosmos stretches endlessly beyond, and within it, the greatest mysteries whisper softly to those who listen. Ahead lies a realm dominated by gravity, so immense that time and space themselves bend and fold, a mysterious kingdom where imagination and mathematics dance together. It is a journey to the brink of knowledge, into the heart of something vast and unknown. Beyond our familiar observations, the universe challenges us with deeper questions. Supermassive black holes, giants at the hearts of galaxies, cast long cosmic shadows over our theories. They are engines of creation and destruction, yet are cloaked in mystery. As we gaze deeper with telescopes and instruments, our data grows rich, but the true nature of these behemoths remains tantalizingly out of reach. Here, where known laws of physics meet the unknown, we find ourselves at an intellectual frontier. We move forward carefully, as if walking on a knife's edge between what we understand and what remains unseen. Each advance in knowledge reveals new puzzles in the cosmic expanse. Even here, standing at the threshold, we sense that something profound awaits beyond. The silence beckons us further. Imagine Einstein, one evening, scribbling equations under the light of a candle. His mathematics predicted objects with gravity so strong that not even light escapes. At first, these black holes seemed unreal, but now they anchor our galaxies. Every answer from his theory only raises more questions about their cause, where space and time end. The event horizon, the point of no return, stands as a grim boundary on our maps of reality, beyond which our theories fall silent. For decades, These giants were mysteries lurking in the dark. Then gradually, humanity built curious machines to observe them. With radio dishes and X-ray telescopes, we saw how matter spirals into the abyss, like water swirling down a drain. These observations painted a canvas of tremendous power. Energetic jets, glowing disks, and sudden flares. Each a clue, but no portrait of the hidden heart itself. In recent years, we have begun to listen to the universe in new ways. We detect faint ripples, gravitational waves, sent from the collision of black holes far away. The first time we heard this cosmic hum, it was as if the universe whispered to us from across the void, confirming that these beasts collide and merge in a silent dance. Each signal is a chapter of a story told at the speed of light, from the edge of known physics. And then, one image captured it all. A ring of fire spinning around darkness itself. A global array of telescopes worked together to reveal the shadow of a black hole at the heart of a distant galaxy. It was a feat of human ingenuity, a cosmic lighthouse and its silhouette, proof that our tools can reach the unreachable. Still, this image only shows the boundary, the edge between the glow of infalling gas and the unseen center. At the edge of understanding, we face a paradox. We measure mass, spin, distance, and energy, yet the core remains a riddle. Inside every black hole lies something Einstein called a singularity, a point where densities become infinite and our equations break down. It is the final frontier in physics, where general relativity and quantum mechanics both falter. We peer at the horizon, but the interior remains an uncharted unknown, a dark secret the universe keeps. Imagine yourself drifting calmly in space, observing a supermassive black hole from a safe distance. In this serene vantage, the cosmos would dance strangely around you. Light from distant stars and galaxies would bend and swirl, painting luminous arcs and rings in the sky. Close to the horizon, time itself would slow down. Moments before our eyes stretch into hours, and the boundary between past and present becomes blurred. Even as reality itself twists, we remain tranquil observers, hearts steady, witnessing the gentle interplay of light and gravity. The black hole, instead of a monster, feels like a silent muse, whispering secrets of the universe. In this vision, the event horizon feels like a gentle boundary. On one side, a riot of glowing gas and light. On the other, pure nothingness. It hangs in space like a dark mirror, reflecting and warping the background of stars into strange patterns. Even in this moment of awe, a sense of peaceful wonder prevails. We know that beyond that boundary lies the deepest unknown, but at our distance, it remains quiet, an invitation rather than a threat. Though we cannot step across that horizon, we may still dream of what lies within. Mathematics tells us of a place where inside becomes outside, where the fabric of space folds so tightly that distances lose their meaning. Contemplating this edge of the unknown stretches our imagination far beyond daily life, and in that stretching, our understanding grows. One might say the universe is courteous. Black holes hide their true hearts behind the event horizon, like a drawn curtain. We watch the show of swirling gas and bending light, but the chaotic singularity behind remains out of sight. It's as if nature permits us to marvel at the spectacle without revealing the strings. This cosmic courtesy both comforts and frustrates us. We know something extraordinary lies beyond, but we must rely on theory to decipher it. These mysteries have a magnetic pull on our curiosity, inviting generations of scientists forward. They collaborate across observatories and laboratories, pooling insight from particle colliders and deep space telescopes. Each question at this edge plants a seed for new exploration, inspiring novel mathematics and fresh eyes on old puzzles. As our tools and ideas evolve, what seems inaccessible today might become tomorrow's breakthrough. At this threshold, the hunger for knowledge feels infinite. There is something profoundly human about standing at these limits of understanding. In a way, every scientist gazing at a black hole becomes a wanderer exploring an alien frontier of mind and math. We feel small against the vast cosmic scale, yet intimately connected through curiosity and creativity. In quiet moments of study, science becomes a gentle conversation with the universe. Some even daydream that black holes might lead somewhere beyond. Mathematics allows, in principle, for wormholes, shortcuts through space-time linking distant regions of the cosmos, or even different universes. These remain speculative and fragile in theory, but the very possibility reminds us how little we truly know. It is as if each black hole holds not just the secret of collapse, but the keys to unseen realms beyond. And yet, even these wild cosmic acts are puzzles to decipher. The signals from colliding black holes and devouring stars arrive as faint patterns in our instruments, enigmatic hints in the fabric of space and time. We are slowly learning their language, but at first they whisper in code. Each observation, each cosmic event, becomes a clue along our path of understanding. In our pursuit, we alternate between elegance and challenge. Mathematics offers elegant frameworks of symmetry and geometry, equations that dance on paper. Yet when we face observations, the universe can be stubborn. The swirling gas, the bending of light, the gentle warping of time all demand that our theories align with nature's script. This interplay of elegance and mystery is the essence of exploring the edge of understanding. For now, we remain at this precipice, at the margins of our knowledge. Each glimpse of truth has only hinted at deeper mysteries below. The quiet frontier beckons, where new, stranger laws may apply. In the darkness ahead, the whispers of quantum questions begin to stir, promising wonders that defy our classical intuition. As we journey from the familiar to the arcane, black holes take on another, even stranger light. They become a stage where gravity and the quantum world meet. Here, the rules we thought we knew begin to change shape. Stepping from the vast cosmic scales to the realm of the very small, physics takes on a surreal character. Particles can become fleeting shadows, and space itself seems to have a jittery dance. In this realm, the whispers of the very small become audible. On the quantum scale, even empty space seethes with virtual particles appearing and vanishing. At the edge of a black hole, these fluctuations can become real. Under the immense pull, one particle of a pair might fall in while its partner escapes, leaving a faint glow of radiation. This gentle emission, known as Hawking radiation, seems to defy the black hole's darkness. It reminds us that even what we perceive as nothingness is alive with possibility. But this evaporation raises a puzzle. If a black hole slowly vanishes, what happens to the information about all it absorbed? According to quantum mechanics, information should never be lost. Yet a fully evaporated black hole seems to erase the details of everything it once contained. This black hole information paradox has emerged as one of physics' deepest questions. It tells us that our current theories are incomplete. Something fundamental is still missing. Theoretical ideas abound to reconcile these puzzles. Consider the holographic principle. The notion that all information inside a black hole could be encoded on its surface, much like a giant hologram. If true, a black hole becomes a cosmic memory, with the event horizon as a protective screen. Others suggest that at the horizon a blazing firewall might wait, disrupting every entanglement with a burst of energy. These ideas are still speculative, but they illustrate how profoundly our understanding is being tested at this edge. Researchers also hope that a true theory of quantum gravity will resolve the paradox. Perhaps in a full quantum description, space inside a black hole never becomes infinitely dense. Some approaches, like loop quantum gravity, hint that a black hole might ultimately rebound, releasing matter in a grand cosmic bounce. Others, from string theory, suggest hidden dimensions and vibrating strings could smooth the collapse. These ideas remain on the frontier of physics, but each offers a possible key to unlock the mystery. Even quantum entanglement might play a role. When a particle escapes and its partner falls in, they remain strangely linked, no matter the distance. Some scientists imagine that by carefully reading these links, the information might leak out in subtle correlations carried by Hawking radiation. In this view, the universe could be using a cosmic bookkeeping trick, preserving what fell in through intricate quantum connections. It's a tantalizing possibility, suggesting that hidden in the gentle glow of radiation is the story of everything that was once lost. At the smallest scales, space-time itself may cease to be smooth. Just as matter is made of atoms, space might be woven from fundamental grains. At these Planck scales, the event horizon would appear less like a smooth sphere and more like a dynamic quilt of quantum foam. In this tapestry, the idea of distance loses meaning, and the line between space and nothing blurs. It reminds us that the universe on its tiniest scales could be even stranger than anything our senses can grasp. Some thinkers describe the universe itself as a hologram, an idea inspired by these puzzles. In this view, the entire 3D reality might be encoded on a distant boundary. Each black hole then becomes a crucial pixel in that cosmic display, with its horizon carrying the data of everything it has seen. It's a powerful metaphor. These dense objects could act like a universe-scale memory, each patch of their surface storing the story of what has fallen in. Though poetic, it reflects real physics. Perhaps at some deep level, space itself is woven from information. Faced with these quantum mysteries, scientists often turn to another tool: simulation. They recreate the cosmos on powerful computers, allowing them to explore what cannot be reached by observation alone. In these virtual experiments, ideas take shape and become testable stories in code. Today, we can build entire universes inside supercomputers. Armed with Einstein's equations and vast computing power, scientists create digital worlds. They simulate galaxies evolving over billions of years, with black holes at their hearts. In these virtual skies, gas flows, stars orbit, and cosmic structures form in accelerated time. By coding the physics into silicon, we unlock secrets that would otherwise remain forever hidden behind the event horizon. These are journeys of the mind. In each simulation run, we watch the unfolding of cosmic events, guided by our curiosity. Consider the first image of a black hole's shadow. Before the Event Horizon Telescope captured it, astrophysicists had already simulated it. They modelled how light would bend around a black hole with the mass of M87. Each simulation produced the glowing ring we eventually saw. These virtual predictions prepared us to interpret the real image. Similarly, for gravitational waves, thousands of computer-generated waveforms of merging black holes allow us to decode the faint chirps we detect. Each simulated waveform is like a fingerprint of a cosmic collision, matching theory to observation. Simulations extend beyond code. Physicists even create analog universes in the lab. Underwater whirlpools, pulses of light in optical fibers, and ultra-cold quantum fluids can mimic aspects of black hole physics. These analog experiments produce counterparts of event horizons and wave emissions. By studying them, scientists test ideas of how horizons affect waves of light or sound. It's as if we bring a tiny piece of the cosmos into the laboratory, observing patterns that would be impossible to capture on galactic scales. Inside these simulations, the details can be stunning. Magnetic fields, braided by swirling gas coil around virtual black holes, launching jets and bursts of energy exactly as we observe in the cosmos. In special runs, when two black holes orbit each other, we can watch the ripples in spacetime that they generate and see how those ripples radiate outward. We are not just theorizing, we are visualizing. In one project, astronomers even used virtual reality to step into a simulated black hole merger, witnessing spacetime warp as a 3D hologram. Such experiences bring the mathematics to life. High-performance computing makes all this possible. Petaflops of calculations run on thousands of processors to model a single black hole collision. In this endeavor, physicists become digital artists, blending code with creativity. The simulations are complex and painstaking. Hours of real time yield only seconds of cosmic action. But with each step, they reveal what might happen when galaxies merge, or a supermassive black hole suddenly gulps down a star. Simulations have grown along with our technology. Early models were simpler sketches, two-dimensional, symmetrical. Today, they are full three-dimensional worlds, capturing turbulence and asymmetries in stunning detail. As computer power increases, so does our vision. What was once sketched on paper is now rendered in pixels and flowing video. Supercomputers become time machines, compressing millions of years of cosmic evolution into hours we can watch and study. Even public software now helps us engage. Interactive programs allow enthusiasts to craft their own cosmic scenarios. Users can tweak parameters and watch galaxies form, collide, or swirl around black holes in real time. Though simplified, these simulations capture the wonder of gravity's dance and bring the abyss a little closer to home. By playing with them, curious minds learn how initial conditions can lead to the grand structures we see today. Machine learning and artificial intelligence have joined the quest. Scientists train neural networks on vast banks of simulated data, so that when a new signal arrives, an AI can recognize the pattern instantly. In seconds, these algorithms sift through endless cosmic scenarios to find the one that matches the observation. This synergy of simulation and AI lets us interpret data faster than ever, turning complex calculations into immediate insight. Yet, even as we build these digital realms and decipher their outputs, mysteries remain. Each answer from a simulation brings new puzzles to light, reminding us that some truths may lie beyond even our best models. We look forward to the questions that await beyond computation, shimmering at the horizon of what we know. Yet for all we have learned, unanswered questions still shimmer in the quiet spaces of thought. We have built tools and theories, but at the center of these giants, answers remain obscured. It is in the hush of pondering that we see the greatest mysteries lingering like stars behind a veil. One profound challenge is to unite the two great pillars of physics, gravity and the quantum. Black holes insist that these laws must coexist, but our current theories clash when pushed to extremes. The true quantum theory of gravity, a framework where space and time themselves have quantum behavior, remains to be discovered. Until it is, the heart of a black hole keeps its secret. Another mystery is cosmic scale. How did supermassive black holes grow so rapidly after the universe's birth? In the early epochs, evidence shows behemoths millions of times more massive than our Sun already existed. The mechanisms of their formation are unclear. Are there hidden processes from the universe's first moments that we do not yet know? Understanding this requires not just studying black holes, but the cosmos as a whole. We also wonder about the unseen. Our universe is filled with dark matter and dark energy, and black holes might be connected. Could primordial black holes formed in the cosmic dawn contribute to dark matter? Could the behavior of galaxies hint at unseen companions? The shadows of black holes brush up against the shadows in our theories, and the intersection remains an open question. In the private realm of speculation, some imagine what could lie on the other side of the horizon. Is a black hole possibly a bridge to another universe? Perhaps the singularity is smoothed out into a new beginning, or maybe information is preserved in some exotic way. These ideas remain on the fringe of thought, but they remind us that nature might hold surprises beyond our wildest expectations. For now, these questions remain unwritten chapters in our story. They watch patiently from the shadows of our ignorance, keeping us humble. Each unanswered question is an invitation, a gentle call to continue our journey beyond the horizon of what we know. And so our exploration presses onward, carried by curiosity into the vast, inviting darkness beyond. As we step back to reflect on our journey through the cosmic landscape, it becomes clear that black holes are much more than empty voids. They are the guardians of the cosmos, anchoring entire galaxies and shaping the destinies of stars around them. In embracing this paradox, we uncover a deeper truth about the universe's balance. And yet, our understanding has deepened. Once seen as mere cosmic monsters, black holes have become symbiotic partners in the tapestry of the universe. They are interwoven with the life of their galaxies, influencing everything from star birth to the dance of spiral arms. As we observe them, even these darkest regions can illuminate our understanding, shedding unexpected light on cosmic evolution. Sometimes, as gas and dust spiral inward, a black hole awakens in brilliance. In these moments of active feeding, it can radiate across the galaxy, launching jets of particles that travel at near light speed. These powerful outbursts heat surrounding gas and can both quench and trigger the formation of new stars, as if pruning or nurturing the cosmic garden. It is a rhythmic ebb and flow, where creation and destruction become two sides of the same cosmic coin. They spend much of their time slumbering quietly, but when fresh streams of matter arrive, the giants awaken with tremendous fury. A quiescent black hole can suddenly ignite, its surroundings lighting up across the spectrum. Then, after millions of years, it will calm again as the fuel is exhausted. This celestial cycle serves as a kind of thermostat for the galaxy's life. When a black hole awakens, it can spark new stars, and when it sleeps, the galaxy grows calm. Beyond their host galaxies, black holes leave fingerprints across the universe. Their particle jets extend far into intergalactic space, blazing trails for hundreds of thousands of light years. These colossal streams become cosmic highways, carrying energy and enriched gas between galaxies. In doing so, they seed the vast cosmic web with the elements needed to form new stars and galaxies, showing how even a black hole can nurture distant realms. For scientists, black holes are cosmic laboratories, holding clues to physics at its most extreme. Inside their deep gravitational wells, the rules of space and time stretch to their limits, revealing phenomena that earthbound experiments can never replicate. In studying these silent giants, we learn more about Einstein's ideas and the fabric of spacetime itself, deciphering messages from the dawn of creation. When galaxies collide and merge, their central black holes can embrace and unite. Such unions give birth to even larger giants, sending ripples through space-time as a cosmic herald of their union. These mergers remind us that even the mightiest guardians are part of an ongoing cosmic dance, forever changing and growing across epochs. Simulations of cosmic evolution have shown that including supermassive black holes makes all the difference. When computer models allow these giants to feed and feedback, the resulting virtual universes look much like our own. Without their stabilizing influence, galaxies would be unrealistic, bursting with stars and lacking structure. This tells us that black holes are not just passive spectators. They are the unseen architects guiding galaxy formation on the largest scales. Our explorations have unveiled these giants across cosmic time, from the distant early universe to our own Milky Way. In each epoch, they stand as sentinels at the heart of galaxies, keeping alive the memory of cosmic history in their depths. In fact, observations tell us that even when the universe was young, black holes already loomed large. Some early quasars had grown to millions of solar masses in place in less than 1 billion years, blazing as cosmic lighthouses in primordial skies. Even with all this knowledge, many mysteries still endure. Astronomers ask how the very first black holes formed from the primordial cosmos. They wonder how these guardians grow in tune with their galaxies, and what unseen forces might influence their growth. Each discovery seems to unveil a deeper puzzle, and so the sentinels of the cosmos stand there, guarding secrets we are still eager to uncover. As we look to the horizon, a new generation of observatories and instruments is coming to life, promising to peer deeper into their mysteries than ever before. Astronomers are building extraordinary new eyes to explore the cosmos, capturing light across every wavelength and even listening to the vibrations of space-time itself. On Earth, we have turned continents into one enormous telescope. By synchronizing radio dishes across the globe, the Event Horizon Telescope became a virtual Earth-sized observatory, capturing the first image of a black hole's shadow. Now, by tuning into shorter wavelengths, its vision is becoming even sharper and richer. The collaboration has extended into higher frequencies that make the images 50% clearer and reveal new colors, unveiling details we could only imagine before. Soon we may watch these cosmic giants in motion, essentially making a movie of a black hole's dance. Beyond radio waves, other instruments are seeking secrets in different lights. The James Webb Space Telescope has already peered back to the dawn of cosmic history, discovering massive black holes feasting in the young universe and providing clues about how they grew so rapidly in those early times. In the coming years, even larger telescopes on Earth, with mirrors as wide as city streets, will zoom in on the hearts of nearby galaxies. They will watch stars dance in the brilliant glow of a black hole's influence, as if a magnifying glass were focused on our galactic centers. In space, new missions will give us entirely new senses. The laser interferometer, space antenna, or LISA, will launch a trio of spacecraft orbiting the Sun, forming arms millions of kilometers long. This fleet will be our first space-based gravitational wave detector, sensitive to waves from black hole mergers thousands of times more massive than those LIGO can catch. It will hear the low, deep murmurs of colossal black holes spiraling together in distant galaxies, opening our ears to a domain of the universe we have never listened to before. Back on Earth, gravitational wave detectors continue to evolve. Existing observatories like LIGO, Virgo, and Cagra are being upgraded to listen for even fainter whispers of space-time distortion. Plans for future observatories envision underground tunnels or supercooled lasers to reduce noise even further. Alongside these, pulsar timing arrays, using the galaxy itself as a detector, have already sensed the gentle rumble of supermassive black holes colliding, hinting at the vast background hum that permeates the cosmos. Meanwhile, scientists are sharpening our vision of the high-energy universe. New X-ray space telescopes will map the hottest gas as it falls into black holes, capturing every flash and flare. Gamma-ray observatories on the ground and in orbit will catch the brightest outbursts as jets plow through interstellar space. Neutrino detectors under ice and water may even pinpoint the most extreme events, catching ghostly particles emitted from the heart of these cosmic furnaces. Together, these new tools form an armory of discovery. Each one is an eye or an ear tuned to the secrets of supermassive black holes. They promise to transform our view of the universe, turning distant mysteries into clear knowledge and whispers from the abyss into a cosmic narrative we can finally understand. In the coming years, our telescopes will grow mightier and more precise. New Earth-based observatories are under construction. Giant optical telescopes with mirrors the size of apartment buildings will gaze into galaxy cores. Radio telescopes will join forces on an unprecedented scale. Projects like the Square Kilometre Array will link thousands of antennae across continents, creating a radio eye so sensitive it can detect the faint whispers of hydrogen in the early universe. With such instruments, we will chart more black hole homes than ever imagined. The Event Horizon Telescope itself will continue to evolve. Already, it has linked telescopes from Antarctica to Hawaii, turning our planet into a single camera lens. Upgrades are underway, adding new sites on mountains across the globe and tuning into higher and lower radio frequencies. This will sharpen the images of black hole shadows, perhaps revealing flickers in real time. One day soon, astronomers hope to not just photograph, but movie these giants in motion, watching plasma swirl and twist around the edge of darkness. Space offers its own vision. The James Webb Space Telescope has given us sight into the dusty hearts of galaxies and the flickering light from material around black holes. Coming space missions will expand this reach. European and Japanese X-ray telescopes are being designed to monitor the highest energy fireworks from black holes. At the same time, new gravitational wave observatories, such as the space mission LISA, will listen for mergers across the universe, while next-generation ground detectors will extend their reach to fainter and more distant events. Even neutrino and cosmic ray observatories may detect the thunder of black hole jets. And even exotic messengers will help. Large neutrino detectors buried deep in ice and water may one day pinpoint a black hole by the neutrinos it emits. And as artificial intelligence combs through mountains of data, algorithms may spot hidden black holes in galaxy surveys or find the signatures of ancient mergers. Astronomy is entering an age of discovery driven by technology, and with each advancement, the horizon of what we can observe shifts further away. The more we look, the more the universe surprises us. Already, every new observatory has uncovered black holes we never knew existed, from dim giants quietly feeding to brilliant quasars blazing in the early cosmos. Looking ahead, we expect to find objects beyond our imagination, perhaps ghostly black holes drifting between galaxies, or the first glimpses of how quantum gravity works near an event horizon. Each new instrument is not just a tool, but a promise that deeper secrets await our discovery. Our eyes are truly on the horizon. There is always more to see. Even as we celebrate the milestones of today's astronomy, we know that the next breakthrough is just beyond the edge of our current knowledge. With every new telescope switched on, the future of black hole discovery brightens, leading us forward into realms of the unknown, still calm and full of wonder, a journey that has only just begun. But even as we see with light and radio waves, another sense is awakening within us. The universe sings to us in silence, a cosmic lullaby of gentle ripples that flow through the very fabric of spacetime. These ripples are gravitational waves, vibrations of space itself that carry the echoes of the most dramatic dances in the sky. For humanity, learning to listen to these gravitational waves is like unveiling a new sense. Suddenly, the sky is not silent. It holds a subtle music in the fabric of space. Each detection is akin to hearing a note from a cosmic violin or the distant rumble of a celestial drum. We find that even the void around us is alive with melody. Imagine black holes as singers in a cosmic choir, each pair contributing a note as they spiral together. Their mergers might be brief and intense, or prolonged and serene, but together they weave a soft, omnipresent murmur. This universal hum is as gentle as a lullaby, one that has been playing since the dawn of black holes in the universe, waiting for us to tune in. For billions of years, as galaxies drifted through space, their black holes have been spinning a silent song. Each pair of orbiting giants hums as they slowly spiral inward, like dancers circling in a ballroom of darkness. Individually, these notes are faint, but together they blend into a majestic symphony that permeates the cosmos. It is a chorus older than humanity itself, one that has carried its tune across light years until it now brushes gently against our instruments. Black holes can crash together in cataclysmic crescendos, but they also produce a quiet symphony. When massive black holes spiral toward each other across millions of years, their collective song becomes a steady hum. Recently, astronomers have finally heard this background chorus for the first time. By precisely timing pulsars, spinning neutron stars that act like celestial metronomes, a subtle, consistent signal has emerged from the data, like listening to dozens of instruments tuning together in the vastness of space. Imagine standing on a shore, listening to distant waves on the ocean. Some waves crash loudly nearby. These are the big black hole mergers that LIGO hears. Others are softer and farther, a steady tide of countless smaller ripples that together create a constant background. Pulsar timing arrays are like giant radio receivers attuned to those low-frequency waves. and they have finally detected the gentle current of the cosmic ocean, showing that the universe's waters have a gentle vibration. This newfound symphony is surprisingly loud, twice as strong as many expected. It suggests that the universe's concert hall is filled with more weighty players than we realized. Each gravitational wave we detect is a note in this cosmic lullaby, some sharp and brief, from stellar mass black holes merging, others slow and deep, from leviathans in far galaxies. When a gravitational wave passes through Earth, space itself stretches and squeezes ever so slightly. Our detectors, like sensitive lasers in vacuumed arms, notice when space-time vibrates. For a moment, those mirrors might move by less than the width of a proton. We have crafted instruments precise enough to perceive that. Each chirp or hum we catch is a message from a distant realm, whispering tales of black holes that collided long ago. On Earth, LIGO and its partners have already recorded the brighter notes of this cosmic melody. Each time a pair of black holes or neutron stars merges, space-time itself shivers, and we hear a fleeting chirp. Those chirps are like a single instrument joining the orchestra, confirming that the universe really is alive with gravitational music. Out in space, future detectors will hear even more. The LISA mission will sense the low, deep bass notes from enormous black hole duets spiraling ever closer. And beyond that, the horizon is broad. We anticipate that every collision, every death dance of stars and galaxies contributes another layer to the soothing, endless lullaby that fills our universe. This cosmic lullaby is gentle and continuous. It carries stories of titanic mergers, but also the echo of things we have not yet dreamed. By listening, we tune in to the rhythm of the universe's evolution, discovering not just cataclysm, but a strange and beautiful harmony woven into the night. For years we have gazed at the cosmos with our eyes. Now we are also learning to hear it. The universe sings to us in silence, a cosmic lullaby of gentle ripples that flow through the very fabric of space-time. These ripples are gravitational waves, vibrations of space itself that carry the echoes of the most dramatic dances in the sky. Imagine black holes as singers in a cosmic choir, each pair contributing a note as they spiral together. Their mergers might be brief and intense, or prolonged and serene, but together they weave a soft, omnipresent murmur. This universal hum is as gentle as a lullaby, one that has been playing since the dawn of black holes in the universe, waiting for us to tune in. For billions of years, as galaxies drifted through space, their black holes have been spinning a silent song. Each pair of orbiting giants hums as they slowly spiral inward, like dancers circling in a ballroom of darkness. Individually, these notes are faint, but together they blend into a majestic symphony that permeates the cosmos. It is a chorus older than humanity itself, one that has carried its tune across light years until it now brushes gently against our instruments. Black holes can crash together in cataclysmic crescendos, but they also produce a quiet symphony. When massive black holes spiral toward each other across millions of years, their collective song becomes a steady hum. Recently, astronomers have finally heard this background chorus for the first time. By precisely timing pulsars, spinning neutron stars that act like celestial metronomes, a subtle, consistent signal has emerged from the data, like listening to dozens of instruments tuning together in the vastness of space. Imagine standing on a shore, listening to distant waves on the ocean. Some waves crash loudly nearby. These are the big black hole mergers that LIGO hears. Others are softer and farther, a steady tide of countless smaller ripples that together create a constant background. Pulsar timing arrays are like giant radio receivers attuned to those low-frequency waves, and they have finally detected the gentle current of the cosmic ocean, showing that the universe's waters have a gentle vibration. This newfound symphony is surprisingly loud, twice as strong as many expected. It suggests that the universe's concert hall is filled with more weighty players than we realized. Each gravitational wave we detect is a note in this cosmic lullaby, some sharp and brief, from stellar mass black holes merging, others slow and deep, from leviathans in far galaxies. When a gravitational wave passes through Earth, space itself stretches and squeezes ever so slightly. Our detectors, like sensitive lasers in vacuumed arms, notice when space-time vibrates. For a moment, those mirrors might move by less than the width of a proton. We have crafted instruments precise enough to perceive that. Each chirp or hum we catch is a message from a distant realm, whispering tales of black holes that collided long ago. On Earth, LIGO and its partners have already recorded the brighter notes of this cosmic melody. Each time a pair of black holes or neutron stars merges, space-time itself shivers, and we hear a fleeting chirp. Those chirps are like a single instrument joining the orchestra, confirming that the universe really is alive with gravitational music. Out in space, future detectors will hear even more. The LISA mission will sense the low, deep bass notes from enormous black hole duets spiraling ever closer. And beyond that, the horizon is broad. We anticipate that every collision, every death dance of stars and galaxies, contributes another layer to the soothing, endless lullaby that fills our universe. This cosmic lullaby is gentle and continuous. It carries stories of titanic mergers, but also the echo of things we have not yet dreamed. By listening, we tune in to the rhythm of the universe's evolution, discovering not just cataclysm, but a strange and beautiful harmony woven into the night. Even now, the cosmic lullaby is incomplete. With each new discovery, a new note will be added to the melody, a new layer to the harmony. We have opened our ears to the universe's song, but we know there are verses we have yet to hear. Our role is to listen with patience and care, so that we can recognize the next refrain when it arrives from the depths of the cosmos. So now, we close our eyes to the gentle hum of the universe. We drift along with its rhythm, comforted by the knowledge that the symphony continues beyond our hearing. Somewhere, the heart of our own galaxy softly contributes a note to this eternal song, and we remain ready, quietly listening, as the universe sings us onward into the next chapter of discovery. At the center of our very own galaxy lies a cosmic sentinel we know intimately, Sagittarius A. From our vantage point, we sense its presence through the swift dance of stars around an invisible giant. Every 16 years, one of these stars races around Sagittarius A in a breathtaking orbit, tracing the outline of its gravitational grip. That swift star dance is proof of the massive, silent guardian at our galaxy's heart. For decades, the center of our galaxy remained a shadowy mystery. Then, astronomers began tracking stars moving around an unseen point. One star, known as S2, swings around Sagittarius A with a period of just 16 years. Observations of its path confirmed that something weighing millions of suns must be there. This was the first direct proof that a massive black hole sat at our galaxy's core. Until recently, This galactic heart seemed quiescent compared to exotic quasars and blazars. But with new eyes, we see that quiet is an illusion. The James Webb Space Telescope revealed that Sagittarius A is alive with flares. Its accretion disk sends out tiny flickers of light that sparkle and fade, and occasionally it erupts in a bright burst. Day by day, our own supermassive black hole pulses with activity, a mysterious beacon deep in the Milky Way's core. Sagittarius A is modest by the standards of the universe's largest black holes. Its mass is dwarfed by the billions of suns monsters found in distant galaxies. Yet its relative quiet and our proximity make it an extraordinary gift to science. It's as if we have a test subject much closer to home. We can study its every move, how gas orbits it, how light bends around it, and even trace how it tugs on the very fabric of time. Our local Sentinel offers insights that distant galaxies cannot. Because Sagittarius A is relatively close, we can study how matter behaves in its grip in exquisite detail. Even a spacecraft placed in its orbit would circle only about as distant as Mercury is from the Sun, cradled by the black hole's gravitational embrace. This intimate proximity means we learn about the very physics at play, how space and time bend, how gas swirls, how jets may flicker to life, all under the gentle watch of a black hole. Looking at the sky, we see evidence of the black hole's past. Gigantic bubbles of energetic gas rise perpendicular from the Milky Way's disk, the so-called Fermi bubbles. They hint that long ago, Sagittarius A may have eaten a large meal, belching out vast jets or winds that inflated these bubbles over tens of thousands of years. This cosmic archaeology tells us that our galaxy's center has a history of activity, and that quiet now could one day break into fury. The heart of the galaxy also teaches us that each black hole is part of a larger cosmic web. Everything in the Milky Way, stars, planets, nebulae, orbits in the presence of this silent behemoth. In a way, Sagittarius A is the heartbeat of our galactic home, its quiet influence shaping the orbits of stars, and perhaps even stirring waves in the gas that cradle newborn suns. Even here, its role is profound, though subtle. This local sentinel is also a laboratory for fundamental physics. By watching the stars near the black hole, astronomers have already tested Einstein's theory of gravity in the strongest fields available. The stars' orbits bend and shift exactly as relativity predicts. The passage of time and the bending of light change subtly in their strong gravitational embrace. Each precise measurement refines our understanding of how space and time behave in extreme conditions. And yet, this exploration is far from over. Each observation of the galactic center reveals new questions. What triggers the flares we see? How will the stars near Sagittarius A evolve? Could the Milky Way's central black hole have once been more active, and will it awaken again? As we discover more about our own heart, we are reminded that every ending is also a beginning. The galaxy still has stories to tell, and we are poised to listen with open wonder. Sagittarius A has a measured mass of about 4 million suns, but it occupies an incredibly small space. Its event horizon, the surface beyond which nothing can escape, is only about 20 million kilometers across. For perspective, that's smaller than the orbit of Mercury. Yet, its gravitational influence extends over many light years, containing a mass equal to 8,000 times that of the nearest star to the Sun. Observations have shown that Sagittarius A flares unpredictably. Sometimes it emits a flare dozens of times brighter than normal, flaring up in X-rays or infrared. These outbursts are thought to come from magnetic instabilities or nearby gas clouds being swallowed. In 2019, a bright flare was even traced, orbiting very close to the event horizon, like a glowing hotspot circling at breakneck speed. By watching these bursts, astronomers can map the immediate environment of our galaxy's central black hole. Our home galaxy also hosts a cluster of stars tightly bound around the black hole. These stars, moving at thousands of kilometers per second, are nature's test particles. In recent years, instruments tracked one star called SO2 as it swung through pericenter, measuring the warping of spacetime as predicted by general relativity. The result was the first direct measurement of gravitational redshift near a black hole, matching Einstein's prediction. Each such observation is like taking the pulse of spacetime itself. Even today, astronomers study how gas and stars settle around Sagittarius A. A disk of young stars orbits in a tilted plane, hinting at past interactions. Molecules in the galactic center are heated by the black hole's energy, creating a laboratory of chemistry unlike elsewhere. The environment is rich with clues: massive star clusters, supernova remnants, and mysterious radio filaments, all animated by the black hole's presence. In many ways, our galaxy's core is an active science lab. If one day the stars in Sagittarius's orbit were silent, we would know not by light, but by their motion. Unlike an ordinary star, a black hole emits no light, but its gravity is an unmistakable fingerprint. By precision tracking, astronomers have effectively seen Sagittarius A through the way it tugs on everything nearby, from long-period gas clouds to fast whirling stars. Each observation is an indirect portrait, painting a picture of the invisible at our galaxy's core. Our galaxy may harbour many more black holes than we realize. Besides Sagittarius A, an unknown number of smaller black holes drift through the Milky Way. These wanderers could have been born in dying stars or brought in by swallowed dwarf galaxies. The Gaia Space Observatory has hinted at possible hidden companions, and future surveys may find these ghostly objects. Discovering them would reveal how common black holes are and how they influence the Milky Way's structure. Although Sagittarius A is relatively quiet today, the Milky Way's center is still restless. A faint glow of X-rays and mysterious gamma rays hint at high-energy activity. Astronomers suspect there may have been past outbursts and even weak jets that shaped the galaxy's halo. Around the black hole, thousands of pulsars spin rapidly, and vast clouds of gas show signs of heating. All these signs make the galactic core a dynamic laboratory, where clues to past eruptions and future fueling reside. For those of us on Earth, this cosmic heart is both an anchor and a reminder. It holds the Milky Way's spiral arms in their graceful rotation, and it reminds us that we belong to something vast. The atoms in our bodies were once part of ancient stars, and those stars were influenced by processes that may have involved the black hole. Every element on Earth was forged in stars that lived and died under the watch of Sagittarius A, connecting us to that central silhouette in the sky. Finally, understanding Sagittarius A prepares us for the future of our galaxy. In a few billion years, the Milky Way will collide with Andromeda, and their central black holes will sway together in a new cosmic dance. By mapping the core of our galaxy now, we learn the steps of that future tango. In every way, our own black hole is a living bridge between past and future chapters of cosmic history. Yet our journey does not end here. The black hole at the center of the Milky Way is both a destination and a beginning. It reminds us that even the familiar still holds surprises, and that each answer leads to new questions. As we continue our exploration, we carry with us the lessons learned from our galaxy's heart, ready to uncover more wonders that the universe has hidden in plain sight. The rhythm of the galaxy's heartbeat guides us onward. Each ripple, each flicker, has added to our understanding, yet we know more will come. The cosmic dawn is still ahead, and we listen quietly, eyes open, as the next movement of this grand symphony begins.